Good morning, everyone on the European time, and good evening and good whatever for those in Indonesia, New Zealand, Australia, or somewhere in Asia or South America. I welcome you to this DEEPEGS final meeting, and I will go very quickly just to introduce ourselves and where we are. Most of you know probably something about the program, but the reason for this webcast meeting is that the COVID-19 pandemic is really taking over, so we cannot be in a meeting room as we planned originally. Now I want to change. Okay, I need to go up. Okay, there's a time delay. Sorry about that. So, welcome to this final meeting. And to tell you a little bit about the DEEPEGS project, it's a demonstration project supported by the European Commission Horizon 2020 program. The goal is to demonstrate the feasibility of enhanced geothermal systems, EDS, for delivering energy from renewable resources in Europe. It's a 4-year project coordinated by HS Orka, which is an energy company in Iceland, in cooperation with partners from Iceland, France, Germany, Italy, and Norway. So 10 partners altogether. There are 5 energy companies. It started 1st of December 2015 and should have ended by November last year. But it was extended for 5 months, so it will end by the end of this month, April. The project was to be testing stimulation technologies for EDS in deep wells in different geological settings and intended to deliver new innovative solutions and models for wider deployments of EDS reservoirs. So the project was meant to demonstrate advanced technologies in 3 different geothermal reservoirs in high enthalpy resource beneath existing high temperature field at Reykjanes in Iceland, with temperature up to 550 degrees centigrades, and in 2 very deep reservoirs in southern France with temperature up to 220 degrees. So that's what we meant to do. And we had 9 work packages, which should show up now. I'm pushing some technical problem in changing the slides.
Go to the arrows at the bottom then on the screen.
Oh, here we are. Okay, I need to go up again. But we had some 9 work packages. Which we don't need to discuss in any detail, but work packages 1 and 9 were about management and dissemination, and then work package 3 on business strategy, going through all 2 technical work packages and the 3 demonstration sites, which are Reykjanes, Valens, and Reykjanes in this diagram. So where are we located on the globe? Iceland is located on the Mid-Atlantic Ridge, and our demonstration site is here in Reykjanes at the very tip of the peninsula, where the Mid-Atlantic Ridge comes up ashore at the very tip of the island, and this demonstration site has seawater salinities, which is fed by seawater. The other places in France, down here in Central Europe, are 4 places actually. We started with Reykjanes and Valens in the south, and then we need to replace Reykjanes by Reykjanes, and then finally all the 3 up to Ventenheim. So on a map of Europe, you see these 3 4 sites, Reykjanes, Valence, and Rion, all in the European Cenozoic rift system, as is Ventenheim here up in the upper Rhine-Graben. So that's most of the discussion in the afternoon will be on Ventenheim, but maybe some of the technical issues down in the other sides. So by this short talk, I give the floor to I welcome you to this DEEPEGS final meeting and ask Sigurður Bogason to take over the panel.
So what I will speak about is some of the issues that we discussed when in the waiting room of the meeting, the housekeeping rules for this webinar, and then also very shortly on how we are learning from our experience, basically from the project, just a few examples and how we see the way forward. So if I move to the next slide, I think I got the mouse back, and I'll just use the arrows. So I was probably speaking on this slide where you see the small diagram or comic. What about the climate? So the housekeeping rules. The speaker panel members have already arrived. We have done a practice run on this webcast, and we would ask the presenters to have their camera switched on so people can see them when they are talking, as your small screen comes with the slide. And try to use wired headsets if possible, because Bluetooth may create kind of a problem. And then mute yourself when you're not presenting. And also remember the lag time. All the attendees have arrived, and then I would like people, and we see some activity already on Slido, that people can ask questions there, and we will try to deal with them as we go along. And basically, we're collecting good questions for the presentation at the end of the meeting today, where we have a discussion panel. And if we get too many interesting questions, we have discussed that we would then add a short meeting without any audience to clear all the questions and splice that to the video that we will share later on, because it depends on the traffic of questions. So it's an animation there. This was at the end of the agenda that was sent out and is available on the website and through many of the social media platforms. The code is there. So then we will also, as I said, will use YouTube to share the proceedings from this meeting later on, so people could view it as a recording later on. And this just to show you, when you enter Slido, you just have to add your name. And this is the history of the live poll. It's people have started to vote for this poll, or you can also go to the audience questions and answers. And we will clear questions in, and you can vote for good questions. If you are, then you don't have to write your own. You just basically say, yeah, I agree with this question, and that pushes them up in our attention. So use this like button, which is in Slido. Just on the lessons, because we are now in DEEPEGS been working for 53 months. And we had high ambitions at the beginning to go further, and we have managed to go further, and that will be in the next talk by Guðmundur Ómar, our coordinator. What we are trying to assess now at the end of the project, how many technologies we managed to move up to TRL 6 or even TRL 7, which is technology readiness level. This will be part of our final reporting to the Commission. And then we have the 2 active demonstrators that will be contents of separate talks. And hopefully we have some knowledge in terms of how to run the geothermal business. So this is an interesting thing that we want to take further. And even though the project is ending, it doesn't mean that the partners are not continuing. So this is just part of the issues. And if I move to the next slide, at the beginning of the project, we had plans for 3 demonstrators bringing in knowledge from earlier work, Reykjanes, Valens, and Strange. And one of the lessons we learned, and which is for European geothermal a lesson to be learned, is that in France there was a slow licensing problem, and that may be also applicable for other countries. So by the end of the day, Valens and Strange did not happen, and we even had in the between another site called Rion. But by the end of the day, our partner von Ross managed to have an existing site that was in works in Vendenheim, and that's the demonstration site that will be discussed later in the meeting. So I think that's more or less the end of this. The project is ending now on 30th of April. Started in December 2015, and we published a number of results, and this is all available on the website. And the next talk will be about the book of publications that we are aiming for. And also there should be by lunchtime at latest 4 posters that's actually a link to the final meeting that people can view from the DPGS website. Because we are trying to speed up because of time zones, not to take a session on the posters in this actual conference. So people are basically directed to go during lunch break and take a look at the posters. So this is the end of my presentation, and this is just a reminder of the upcoming agenda points for this session and the lunch break. And I will hand now the mouse over to my colleague, Alicia. So when you are ready, you just take over, because your presentation is part of this one now.
Hello, everybody. I think you couldn't hear what I was just saying for a second. I would like to introduce the DPGS book of publications we are preparing, and it will be available soon after the meeting. And the book of publications aims to acknowledge the scientific work achieved by DPGS researchers team during the lifespan of the Horizon 2020 funding. We will promote it using the hashtag DPGS publications, and under this hashtag you can find a lot of already informations, and as well be directed to the main website where the scientific work is the public part is public. The book of publications covers 4 interesting parts, which is key findings of general project itself. About the second part is about the site in Reykjanes in Iceland, and the 4th part consists of the Vendenheim site in France, and 3 other sites which were as well developed beforehand. The other chapters are based on the journal articles, conference proceedings, and conference abstracts. And this work published by scientists working during 2016-2020. Book of publications gathers the information from scientists who attended 35 different conferences, all over 35, and as well issued more than 148 scientifically acknowledged documents in past 48 months of project durations. In chapter 1, we will gather all the scientific journal articles, which we have already 9, and approximately 2 or 3 are currently as well in the reviewing process. And they were issued by 6 different journals. The chapter 2 focused on the conference proceedings, which we gathered 51 of them, including over 30 conference proceedings for the World Geothermal Congress, which will be introduced next year due to the postponement of the event. The chapter number 3 focuses and gathers all the conference abstracts, which scientists gather approximately 25 already issued in 17 different worldwide conferences. As the last part, and you can find this information mostly on online on our website, we are gonna to share as well all 63 public deliverables, and you can have a glimpse on the media articles which we officially produced, and they're officially in cooperation with worldwide and media, and these are approximately 20 articles. And we are encouraging you to follow us and check especially the website for all the scientific job which our scientist has achieved during this years of cooperation. Thank you.
So I'm going to give you a brief introduction to the Reykjanes demonstration well, sort of progress overview. And I am the coordinator for the DEEPEGS project with this logo, but also a PI for the Iceland Deep Drilling project, which has this logo here. So the well is called IDDP2, as part of the Iceland Deep Drilling project, but in this case, intimate part of the DEEPEGS project. The next slide should be coming up. I don't seem to be in control here. Okay, next slide. So as I said before, Iceland, we are located on the mid-Atlantic ridge at the very southeast western tip of Iceland. And the geothermal system is fed by seawater salinity. So it's a high temperature system within the rift zone of Iceland. And if I just present you a very simple, no, this is a picture of the rig on site. The well was drilled in 2016 and early 2017. And this is at the rig site. We had a viewpoint for general public with some information about the DEEPEGS project, what we were doing, who were the key players and so on, so people could access and watch it from a safe distance, the operation. And quite a few people visited us during that time. So in a very simple conceptual model, in high temperature fields, we have magmatic or either cooling magmatic intrusions, which are then simply hot intrusions, or liquid intrusions, if it is magma, which are fed, conducting heat upwards to conventional high temperature systems at upper part, but our DEEPEGS project is down at the intersect where we have brittle ductile transition. Most of the high temperature systems on land are fed by meteoric water, but in our case, our system is fed by seawater recharge. And in this regime here at the brittle ductile transition, which may be quite shallow, but in our case, closer to 6 kilometers. Our target is this green field here on a temperature depth diagram beyond the critical point in temperature regime 400 to 600 degrees. And we succeeded in drilling into supercritical condition with our drill hole. This is a map, geological map of the demonstration sites, which is mostly covered by Holocene or young lavas. The youngest one is 800-year-old. And our drill hole is located just about here, and we sidetracked it into the center of the drill field. Here is a cross-section, the resistivity cross-section. And our drill hole is beginning in the background and then coming out into the field of view here with this bar here. And we know the upper part down to say 300 degrees with mineralogy and temperature logging. And we expected to drill into amphibolite facies rocks above 450 degree hot. And this green plum here is lower resistivity than the blue on both sides. So we were hoping that this was the upflowing channel for the supercritical, for the Reykjanes high temperature system. We know the geology on the uppermost, say 2.5 kilometers, mostly hyaloclastite and marine sediments, and then pilobasalts. And as we go deeper, we get increasingly greater amount of seated dikes or dikes. And we expected to be drilling a seated dike complex similar to the ophiolite oceanic crusts. And as we drilled on, we proved right, so this model kind of holds. We knew the temperatures roughly down to say 3 kilometers and expected to be in 500 degrees somewhere close to the end, but with a little higher. And this is a picture of Reykjanes showing you it should be moving. I need to go back to it. Just push the button here. No. This was meant to show you no, it's not working. Okay, patience. So you see here the deep well, which is in violet, and the rest of the drill holes in the field, some of them are sidetracked, others are straight. And you see our deep well is 2 times deeper than the rest of the drill holes. And it is cased to almost 3 kilometer depth, so beneath all the other production wells. So we are in a very strategic place where we could affect the overlaying geothermal field. And this well is called IDTP2. So we drilled the well in 168 days. And during the drilling, we attempted to take core samples, spot cores, some 13 times, and had a very good success with quite a few of them, especially at the very bottom of the well, which was very fortunate because we got a lot of information from there. And we used 3.5-inch drill string for stimulation, deep stimulation of the well after close to the end, or after the drilling itself. And in these cores, you will hear 2 talks about these cores. You can see here on the left, on the right, say coarse minerals, fluid inclusions have been studied by Enrico Bali. And in the course, a lot of petrology, which Robert Schierenberg will describe to you. But during the drilling, we had a lot of technical devices like fastened cables with thermocouples from Petrosbek and also from GFZ, a fiber optic cable down to 800 meters. The others went down to almost to the bottom of the well. This, you will hear talk about this, research from this. And we also put down for the first time in Iceland very sophisticated downhole logging while tripping, we say here, logging while drilling tool, which was inserted at the end of the 8.5-inch drilling. And in our next talk, you will hear the research from this magnificent tool here. So there's a lot of first in this drill hole. Following the agenda, after these three presentations, we will have three short presentations on seismicity, tracing fluid, and then discussion on the most likely fluid conditions. And then followed by three presentations on the design and construction of the wellhead and flow line, followed by expected fluid contribution from different zones, and the attempts to get the well flowing. After a short lunch break, we will then start again with 4 presentations on innovations that have resulted and been developed within DPDS and some earlier EU-supported programs or projects. So our plan was to finish before 2020. We added 5 months to that, and our plan was to do the stimulation, finish the drilling and do stimulation in 2017. And to flow testing in 2018 and pilot studies for energy production in 2019, but both of these were delayed for several reasons, and so the flow testing hasn't really started. But we have a lot of information from this drill hole, and I will just, and you will hear about that this morning, but I will just make it clear that the main economic research for the Reykjanes demonstration is that the conventional high temperature reservoir almost doubled in volume due to proven deep permeability. So our drill holes are mostly being permeable about, say, 2.5 kilometers, but we have now a proven permeability down to 3.5 kilometers at least. So we have to add a kilometer to this to the conventional system, which is amazing, doubling the volume, just like that. This means that the company can, if they like, drill deeper well to get more of the conventional high temperature steam. But then below roughly 4 kilometer depth, we are in supercritical regime at 400 to 600 degrees. And we lost all our circulation fluid all the time, and know that there are a lot of permeable fractures down to the very bottom of the well. So it is quite clear that we can create a deep EDS system, mining heat from the very hot rocks down here and providing pressure support to the overlying system as well as temperature support. So this will undoubtedly extend the lifetime of sustainable energy production in the Reykjanes field. So this is very economic benefit for the company that is dealing with this, and undoubtedly for other companies in high temperature regime to see this great permeability in the supercritical regime as well.
Good morning, everyone. I am Johan Alexandru Merciu. I'm a researcher at Equinor in Norway. We thank for the opportunity that we have been given to look into this very unique data set. And we want to thank from the beginning to the organizers and to everyone which was involved from financial and operational and scientific point of view in this project. I think what we are about to see is pretty unique. Up to our knowledge, this is the first time someone was able to deploy borehole geophysics and borehole geophysical sensors in such conditions, which will provide a very stiff learning curve for the geothermal industry. We are on the way to show you a presentation which is split in two. One part of the presentation will deal briefly with the quality of the data acquired, and the second part with an opinion and interpretation of the data that we have been provided into this in this project. Okay, jumping a bit too fast. The data acquisition was deployed in extremely complex borehole conditions. As was mentioned before, there were a lot of losses. There were a lot of struggling during drilling, which kind of exposed the borehole for a long time, and borehole downhole sensors that they were deployed, they were not exposed to what one will call a standard exposure, which actually provides some limitation in terms of borehole corrections that you need to apply to the data, and extremely difficult to understand actually what was the exact system which was placed in between the face of the sensors and the borehole. That is to say, if you go in with a very cold fluid which interacts with very hot fluids and hot rocks, we don't know what is the actual status of the material in between the sensor of the tool and the rock. So that's the major thing that we encounter here, and simply we don't know. So therefore, we are not very confident in terms of quality of the borehole correction which are applied on the data, and then we embarked into a best guess situation, and we believe that we have recovered a lot of the information that at the first sight may be difficult to grasp on. In terms of data and data quality control, there is a lot of data which was collected in this project. Comparing with the oil and gas industry, what we have seen is that the geothermal has a lot of room and a very important room for improvement in terms of standardization of data delivery from the boreholes. So I believe that what this IDTP2 is teaching us, it's teaching us for the future about data manipulation, housekeeping, and things like that. Here is an example of how the data sets may look like, right? When you start to go into a database, you may have a plurality of formats. You may get things that you may not be familiar with, and you will have to learn your way out of that. For one reason, is jumping 2 pages at one time. Let's see. If I manage.
It was a time lag. You click twice. Be careful.
Yeah, I click once. What we have done, we have placed in all the data set into one database. So everything what we have received, we placed it into a database, and we have chosen to use the simplest standard oil and gas software that we have, which is called WellCAD. Right, and we have performed the data manipulation under WellCAD. There may be some parts of the data sets which we may have used Excels or some MATLABs, but the main software we have used is WellCAD, and we have done that because the WellCAD is kind of a software which is built for geothermal and the mining industry, and it will find a lot of users at a low cost for future projects. However, you can manipulate the data in any other softwares like Techlog, Geolog, and any other data spaces and IT solutions. I let in this presentation for the public and the colleagues to view how the data was recorded, but I will not go over it. The digital data was imported, and then we have made some first look into the borehole images, which are the most important part of the data, and the borehole images that are collected at IDDP2 are the data sets which are extremely rich in information, and one can take the information and perhaps try to do a different kind of interpretation on those data sets, but they need to be aware of the restriction on the quality control and the things that we have just mentioned before. Into a first side, we have made an effort with the colleagues from France, Peter Boire, for example, and we have published a trial on explaining certain artifacts and certain image interpretations that we have seen into ultrasonic logs. And then try to learn from ultrasonic logs what is the image and what are the images behavior, and then translate that kind of knowledge towards the resistivity part of the borehole image data that is collected. We have done that because the ultrasonic is collected down to about 3,000 meters, 3,200 meters, while the resistivity data from LWD is collected down to the bottom of the well with some gaps. Therefore, we need to kind of accommodate ourselves in terms of interpretation and provide some sort of correlative and background check from the ultrasonics to the resistivity image. This is a good exercise, and this is very, very, very good thing that the IDDP2 has managed to collect ultrasonic and resistivity data in parts of the well, because that kind of gives us some confidence in terms of how the images look like, what could be the aspects of correlation between the two different physics which are deployed. Yes, try again. We are moving now to the second part of the presentation, and we have to remind the people working with borehole data that we are focused on borehole images and not on the rest of petrophysical data which may be collected. And the scope of the borehole image logging kind of touches many aspects of reservoir engineering from all points of view. We have used this information to provide scientific evaluation and drilling efficiency for geomagma projects. So we have tried to correlate the information that we have extracted from the borehole images also with the drilling. That is a way of looking at finding anchors in terms of quality of the data and the information which is hidden in the borehole logs, to constrain the uncertainty that is generated from the fact that we don't really know the actual borehole condition in those extreme conditions. We have done two types of investigations based on two different physics. One is ultrasonic physics. I will not go much into the detail of that. What we have done for the ultrasonic images was to look at, so this is the raw information, you see it here on the left, and then we process the data in such that we are eliminating a bit the centralization effect, and then we enhance actually the picture of the wall. So the centralization remains very prominent across the pictures and provides with kind of artifacts in terms of vertical white and black stripes along the vertical side of the image. Also, the caliper is not necessarily perfect, but still we managed to get some information about the shape of the borehole and possible breakouts. For the resistivity part, which is the LWD Weatherford tool, we have done a standard static and dynamic imaging, and then we look on the image complexity mapping, which in principle it's an anisotropic diffusion technique applied to the borehole images, and then we obtain 3 additional maps here posted on the left track of the images. So one for the raw image, one for the static normalized image, and one for dynamic normalized image. In general, the service companies will provide you with the static and dynamic image without looking into actual statistical behavior of the information inside the image. Therefore, we have tried to expand a bit and look from a different angle on the information contained in those logs to see if there is any usable information actually to be used in order to constrain our main quality concerns, again related with the borehole conditions. And what we have found out was that when you look across the image is that we can perform a zonation of the image from top to bottom. So at the top here is the casing shoe, the 958 casing shoe, and here is the TD, or the deepest part of collected LWD data. And then we were able to provide consistent zonation. So you take from the casing shoe around 2,940 meters, and then you go down, and then we observe that there are certain ways that one can actually zonate the intervals across the borehole. What is interesting to see is that this picture teaches us that the material above this interval, 3,700 to about 3,900 meters, looks from a dynamic correlative point of view very similar with what is below. And that's a very important key message that we have to give to the project. Saying that whatever material is here seems to be very homogeneous, except what is happening here about 3,700 to about 3,900 meters depth. And then we start to zoom in to learn a bit about the properties of that that part of the image. When we zoom into the image, we observe that the image kind of tells us a story of pillow lava, right? And we manipulate the image in such way that we could enhance the contrast inside the image, and then we can see those lobulars artifacts inside the image. And this is pretty much a correlation with databases from ODP experiences and from other places like Hawaii, where they have encountered similar borehole images, but at very shallow intervals, right? So, and that kind of gives us more information about what could be the actual history of this interval. We have done also an exercise where we have plotted the drilling information on another column, and by drilling information we just refer to what the people were collecting at the drill shack, saying that okay, from this depth we have a softer rock, a harder rock, because they didn't have mud returns, then we need to simply rely on those observations and wait on beats and ROPs. And then we made a map showing that there is a clear transition at this depth and at this depth, which pretty much encapsulates the depth where we observe those, let's call them pillow lavas. And that kind of gives us more confidence that actually the information from inside the resistivity log is it's usable to a certain extent. We have done then a full interpretation of the feature intersecting the borehole, and then we have simply displayed inclination azimuths of those features, which we may call them fractures, right? But they are not necessarily fractures. And we see that there is a general trend of intersecting the boreholes at about 90 degrees, but then in this interval, there is a bit more chaotic displacement of the features. And we have done this exercise for the entire length of the borehole with the hope that we will be able to say something about the fracture distribution across the borehole. We also looked a bit into a full integration of the data sets. This work is not completed yet. Perhaps after this meeting, we may have more insight about the mineralogical aspects of the borehole which is encountered by the borehole. In this example, we have the raw image from the resistivity. We have the temperature profile of the borehole, where we took a second derivative of the temperature along the borehole. And we observe that, again, we have a zero gradient across this, let's call it pillow lava interval, which kind of separates the borehole in two independent intervals. And then we plot also the core images with the hope that we can perhaps orient the course at a later stage. We also provide opinion related with the interpretation of those logs. In principle, the opinion is cross-corroborated between ultrasonic image and the resistivity image. And we have performed interpretation for all the zones that we have depicted from the static and dynamic normalized windows in ICM flags. And I let inside the presentation all the intervals with their density of the fracture, so then one can have a look into them and learn about what we have seen from the LWD. To give you an example, I will just pick up a random one. In this 3,900 to 4,100 meters, the interval is entirely characterized by presence of drill-induced breakouts and tensile fractures overlaid with petals, which is saying that the borehole did not encounter many aspects that we can interpret them as fractures, but more aspects which can be interpreted from a drilling point of view, which indicates a very borehole condition where you are in a situation which is underbalanced. So the pressure inside the borehole is less than the pressure or the minimum stress of the rocks surrounding the borehole. And to enclose our interpretation, we have tried to make the general picture to give you an understanding of how we look at the data. So, and to give you some sort of timeline of the development of those parts of the encountered by the borehole, we have seen that from top to bottom it's a sheet dike complex. And we believe that this was first in place, but then there is a magmatic event happening post-dike in the evolution, which kind of intersects the dike structure, and we see that also from the inclination azimuth of the possible fractures, and we see that this kind of explains in a sense what's happening with the interval between 3,700 to 3,900 in this well. And we have done also a quick check against the literature, and we believe that you are inside of a sheeted dike complex with very little indications of intersecting a brittle zone. That's our presentation. Again, we thank so much for the support and for the data, and we are opening for questions, I guess, at this stage.
Good morning, everyone. It's my pleasure to talk to you about the alteration of the drill core which we collected. You can see my list of co-authors here. Why are we interested in the alteration? Well, of course, we really would like to know what the fluid composition is at the bottom of the hole and the fluid temperatures, but we haven't been able to produce those yet. The alteration minerals tell us something about what's going on downhole, and I want to present what we think we know about this so far. So my slide isn't advancing. Let's try it this way.
It's a time delay, so the mouse arrows at the bottom. Yeah.
There we go. On the screen in the middle, you see a representation of our drill hole, the IDDP 2 drill hole, and also shown to the left are some of the deeper holes drilled through the oceanic crust by the Ocean Drilling Program, and realize that these are all started at the rock surface. So if we put these 2 kilometers or 2.5 kilometers below sea level, they're all at about the same depth at the bottom of the hole. And that depth is about 4.5 kilometers in what we think is the deep reaction zone of an ophiolite type system. As you've heard, we did not recover cuttings from these, so our knowledge is limited to the cores. We had previously cored in the reservoir at Reykjanes, and I want to talk about these deeper cores. I'm going to focus on these cores down here. I'm going to define these as the amphibole zone. And at the very bottom of the hole, we had 3 cores, almost continuous recovery, 20 meters. I'm going to call this the pyroxene zone. And so let me tell you what we found. Basically, everything we saw was sheeted dikes. Everything we covered was sheeted dikes. And here's a typical example. And what you see is a nice igneous texture, with the lighter being the plagioclase and the thin section view. And what was clinopyroxene is now replaced by hornblende, a calcic amphibole, and then some magnetite and ilmenite. Most of the rocks we recover are almost unfractured. You can see there's one small fracture here, and in the thin section, you see a small fracture filled with hornblende. And so these rocks look, they preserve their igneous texture, they look very impermeable, yet they have been pervasively altered. There are essentially no igneous minerals left. All the original igneous pyroxene has been replaced by hornblende in the upper zone, and the plagioclase has changed composition. So these rocks have been pervasively altered, even though they seem fairly impermeable. I want to focus on the deep zone, and on the left side of the screen, you see a thin section view and plain light and polarized light of, again, a diabasic texture with what was igneous clinopyroxene and plagioclase. But again, there are no primary igneous minerals here. Everything has been recrystallized and replaced. And now, in addition to the hornblende, which we saw in the amphibole zone, the hornblende is intergrown with clinopyroxene and orthopyroxene, but both of these pyroxenes are not the original igneous pyroxenes, they're hydrothermal pyroxenes. And in the dark in this backscattered image are the plagioclase crystals, which are the light and thin section. And so these rocks, again, retain their igneous texture more or less, but have been completely replaced by a high temperature mineral assemblage related to the hydrothermal alteration. So looking at several other backscattered electron photos, most of the minerals we see are minerals that we associate with igneous rocks. In the bottom most core, the last 3 cores, we collected 4 half dikes separated by chill zones. One of them had olivine phenocryst, and you see olivine remaining here, but this olivine has been hydrothermally recrystallized, and so it has a much higher iron content. This is not the original olivine. You can see here it's been overgrown by orthopyroxene. That's because when the fluid started interacting with the olivine, brought in silica and stabilized orthopyroxene, and then in the background we see the normal alteration. It's important to note that the olivine and the orthopyroxene, which are hydrothermal minerals, have not been altered to hydrous minerals like talc or serpentine. The general assemblage you see, again, is hornblende, clinopyroxene, orthopyroxene, all hydrothermal and intergrown with iron oxides, ilmenite, and magnetite. Locally, we see some recrystallized texture, what looks like a metamorphic texture, but I've emphasized that because we have core and we can see the paragenesis, this is not contact metamorphism, this is actually hydrothermal alteration. And then in the uppermost part of the lower cores, we see a later stage of biotite that's replacing some of this. Well, luckily, some of these minerals can be used as geothermometers. So coexisting, touching pairs of clinopyroxene and orthopyroxene, we can analyze them in an electron microprobe and get a temperature. And this is 236 analyses giving temperatures. You see that the average temperature of the pyroxene alteration is 825. We can also use the composition of hornblende and plagioclase. And again, you see we get a lower average temperature, but notice that the clinopyroxene, orthopyroxene, which is a little earlier, is skewed to high temperature. The amphibole plagioclase is skewed to lower temperature. And it's really the median temperatures that are similar, and they're forming at the same time. So these rocks are getting pervasively hydrothermally altered at temperatures like 800 degrees. Common wisdom is that fluid doesn't get into rocks above the brittle ductile transition, which would be about 600 degrees, yet these rocks are pervasively altered by hydrous fluids. I'm going to skip over this slide for the sake of time. And I want to sort of take you through the temperature alteration history. Because we have core and we can see the paragenesis, we know that the initial phase of alteration to clinopyroxene and amphibole plagioclase happens at about 800 degrees. But hydrothermal circulation continues and we can see cooling of the rocks. We can use the amount of titanium and quartz as a different geothermometer. Quartz in these rocks is very rare, actually. There's not much quartz. And it occurs in a lot of different paragenetic stages, but you see we get some very high temperature quartz, and I'm going to focus in on the low temperature quartz because this tells us what we think is the present day temperature. Again, in part of the rocks, we get this biotite zone, and the biotite form later, and you can see it forms at a very uniform temperature using the titanium and biotite about 700 degrees, and that's similar to the peak in the quartz titanium, and they form together. There are very few veins in this, but there are some veins and they're important. One of the veins has, the veins are mainly quartz and plagioclase. One of them has case bar. That gives us a different geothermometer, shows us a lower temperature. And then the pair magnetite ilmenite shows us the lowest temperature yet. And because this geothermometer does not freeze in, it continues to re-equilibrate. So we think this geothermometer, you see a very narrow peak, that's about 600, is becoming closer to what we think the actual borehole temperature is. Again, this shows the magnetite ilmenite geothermometer in the pyroxene zone. We go up to the amphibole zone, the magnetite is preserved with igneous texture and doesn't give us temperatures. We can only use this geothermometer in the lower temperatures. And again, this shows us the quartz geothermometer. On this thin section, the yellow is, this is a luminescence photo. The yellow is plagioclase in the igneous texture, and the brown is the pyroxene earth things. Here is a vein with plagioclase and quartz, and the temperature, the spots represent probe spots, and you can see this vein, the quartz formed at about 700 to 750. But I want to focus in on this quartz grain, which came from the latest stage. The one open fracture in the latest stages was a euhedral quartz crystal. And you can see that it started forming about 650, and the lowest temperatures we measure in this quartz are just a little below 600. And these are the same quartz crystals that you're going to hear fluid inclusion data on in the next talk from Enna Cobell. And they give the same kind of temperatures. Okay, so this shows that one open fracture. You can see that here's the altered rock. This is the vein of quartz plagioclase case bar, and then this open fracture. The orange staining on this is all secondary related to drilling. When you cut this rock, you can see at the top, there's no orange staining. So this was formed because there was iron-rich fluid in the drill hole that was being oxidized during drilling because of pumping cold water. We look at this open fracture. We see it's coated with hydrothermal euhedral biotite, and the biotite is overgrown by this euhedral quartz. This is the latest stage we see. And Again, emphasizing that when we cut this core, we don't see this red staining because it's superimposed by the drilling. But when we cut this core, this vein, which is this, was bright white. But as the core dried after washing, it became yellow because a salt precipitated out from the pore fluids. That salt is a potassium iron chloride salt, and we see the same minerals included in the fluid inclusions in this core. And so the fluid inclusions are sampling a high salinity brine with high potassium, iron, and chloride, and that fluid is still present in these rocks and was flowing into the drill hole when we were drilling. And again, using the paragenesis, the temperature in this vein from the quartz plasma case, 657, the later quartz biotite gives us an oxygen isotope temperature a little lower, the latest phase in the titanium 600, and again, the fluid inclusion 600. So using the paragenesis, we can not only get temperatures, but we can see the temperature time progression in these. Okay, so to summarize sort of the temperature data, I've been talking about the pyroxene zone, and now I'm just plotting the median temperatures rather than the distributions. And what we see is that the initial alteration to pyroxene and amphibole occurs about 800. In some of the rocks, we get a second event superimposing biotite and quartz at about 750. And the magnetite ilmenite geothermometer continues to re-equilibrate down to the lowest temperatures and gives us the lowest temperature. The only geothermometer we can apply up here in the shallower amphibole zone is the amphibole plagioclase geothermometer, and you can see that this gives us a nice geothermal gradient, which is about 100 to 120 degrees, maybe higher at the base, and that suggests that if we had a magmatic heat source, it was at a depth of something like 1.5 to 2.5 kilometers below our drilling at the base of 4.5 kilometers. And we did measure temperature and pressure in the hole before that last coring. The blue shows the pressure record. The pressure record was determined by the head in the drill hole, which is determined by how much water we were pumping in. So this is imposed on the drill hole. It's not the in situ pressure. The pressure was 340 bars. And the temperature record goes up to 426. It turns out that at this temperature and pressure, that is exactly on the two-phase separation curve for seawater, and it's because we had 600-degree seawater coming in, phase separating in the bottom of the drill hole, and that's what set the fluid pressure. So I'll finish the talk there. I'll leave these conclusions up for you to read. Thank you very much.
Welcome everybody. I will talk about the composition and the properties of the geothermal fluid at the deepest part of the borehole. I am the presenter, but this work has been done in collaboration with a number of research institutes. I'm not sure that I can change my slide. For some reason, I can't change. Okay. So this work has been done in collaboration with a number of research institutes, including universities from Hungary, the United States, and Switzerland. So before this talk, the borehole has already been introduced in detail. We know that the vertical depth is approximately 4,500 meters. The fluid pressure estimated to be at the bottom approximately 340 bars, and the temperature based on borehole measurements is estimated to be at least 535 degrees Celsius. We have just heard that based on alteration mineralogy, the temperature could be higher than this. In any case, if we take a look at the phase diagram of water NaCl system here on the right hand side, any of these conditions suggest that the fluid at the bottom of the borehole is in supercritical condition. In order to confirm this, we decided to take a look at fluid inclusions, which are tiny droplets of the geothermal fluid trapped as inclusions in minerals. And we planned to determine the physical state, the temperature, and the composition of the geothermal fluid at the bottom of the borehole. For this, we used file sequence from core 11, which has been drilled between 4,634 to 4,635 meters depth. If you take a look at these file sequence and the fluid inclusions in detail, we could distinguish primary and secondary fluid inclusion assemblages. The primary fluid inclusion assemblages can be seen here on the left-hand side. They are trapped along growth zones of crystals, and they are coeval with the development of these file sequence. In contrast, secondary fluid inclusion assemblages, what we can see here on the right-hand side, are cross-cutting grain boundaries. They are post-dating the development of the file sequence themselves, and they are representing the latest stage of fluid movement within these cores. So this study focuses on the study of the secondary fluid inclusion assemblages because they are the most representative of the current geothermal fluid at the bottom of the borehole. If we take a look at these fluid inclusion assemblages in detail, in all secondary fluid inclusion assemblages, we could observe different types of fluid inclusions. Mainly, we could observe vapor-rich and brine fluid inclusions. You can see vapor-rich inclusions with a large vapor bubble and a thin liquid film around it. And in the same fluid inclusion assemblage, you can also observe another type of fluid inclusion, which contains lots of different types of fluid and a large vapor bubble. These are brine inclusions. They are sitting just next to each other. Besides this, we could observe also occasionally a third type of inclusions, which are silicate melt inclusions. You can see one here in the left-hand side. These silicate melt inclusions are composed of a felsic silicate glass and a vapor bubble. And if you take a look at the picture on the right-hand side, you can see that this large silicate melt inclusion is sitting in the same fluid inclusion assemblage as these vapor-rich inclusions. And if we change the focus, we see that some brine inclusions are also associated with these silicate melt and vapor-rich inclusions. Now let's take a look at the composition of these inclusions a little bit in detail, and we start with the brine inclusions. All brine inclusions composed of dominantly two types of iron potassium chloride hydroxide with different stoichiometry, a sodium chloride potassium chloride solid solution, and all brine inclusion contained an iron copper sulfide phase. In minor amount, we could observe iron chloride hydroxide, barium chloride, calcium chloride, and apatite in these fluid inclusions. When we started to reheat these fluid inclusions, the last solid, which was the sulfide, disappeared in all fluid inclusions around 600 plus minus 20 degrees Celsius. At this temperature, all brine inclusion composed of a hypersaline brine and different sizes of a small vapor bubble. If we take a look at the vapor-rich fluid inclusions, they were dominated by H2O fluid. Most of them contained more than 95% H2O, with CO2 as the second most common volatile phase, traces of H2S and hydrogen. When we heated up these inclusions, they homogenized into the vapor phase at 600 plus minus 10 degrees Celsius. If we take a look at the silicate melt inclusions, here you can see a backscattered electron image where silicate melt inclusions and vapor-rich inclusions are sitting in one fluid inclusion row. These silicate melt inclusions are rhyolitic in composition, and interestingly, the potassium to sodium ratio in these silicate melt inclusions are above 1.5, which is unique in Iceland. All rhyolites in Iceland are sodic. Based on the fact that the vapor-rich inclusions homogenize to the vapor phase at 600 plus minus 10 degrees Celsius, and the last solid disappears in the brine at exactly the same temperature, we can conclude that the temperature of the geothermal fluid at the bottom of the borehole is approximately 600 degrees Celsius. This is in line with the lowest temperatures what we got from the mineral-based geothermometers. Based on the presence of these inclusion types, we can also conclude that there is no one single supercritical fluid at the bottom of the borehole, but the fluid is separated to an H2O-rich vapor and an iron-potassium-rich brine. We calculated the enthalpy of the vapor phase, which is likely to be 60 kilojoule per mole. What else do we know based on the homogenization experiments? We can also calculate the pressure where these fluids have been trapped. If vapor-rich inclusions homogenize at 600 degrees Celsius and the sodium chloride dissolves in these fluid inclusions at around 390 degrees, based on the behavior of the sodium chloride water system, we can assume that the entrapment pressure of these fluid inclusion assemblages was something close to 50 to 60 megapascals. But we have seen that these fluids are not pure sodium chloride water fluids. They contain significant amount of iron chloride, which changes the phase boundaries in the system. We don't know exactly how much it changes, but based on our current knowledge, we can establish that the pressure at the bottom of the borehole is likely to be close to 45 megapascal, which is equal to the cold hydrostatic conditions. Now let's take a look at the trace element composition of the fluids, and unfortunately, even if I change this, the bottom of this diagram is not visible. On the x-axis are lined up the different trace elements. We analyzed 28 elements in both brine and vapor-rich inclusions. In this diagram, these concentrations are normalized to seawater. So the composition of seawater here is indicated by this black line in the middle. The brine inclusions are the filled symbols and the vapor-rich inclusions are the open symbols. But we can see here that all major and trace elements are partitioning into the brine. And we can also see that many of the trace elements, both in the brine and the vapor-rich inclusions, are enriched relative to seawater. Base metals, copper, molybdenum, zinc, which are plotted here, and noble metals, aluminum, gold, and silver, which are plotted here, are enriched in the brine 7 to 9 orders of magnitude compared to seawater. And they are also significantly enriched in the vapor phase. If we compare the composition of these inclusions to the composition of the geothermal fluid sampled at shallower depth in the Reykjanes field, we can see that the vapor-rich inclusions are very similar in composition to the fluids which are measured at 1350 to 1650 meters depth in other boreholes. And of course, all fluids are enriched in all trace elements compared to the composition of the geothermal fluid which has been sampled at the wellhead. I would also like to point out that these are the chlorine, bromine, boron, and sulfur compositions in the geothermal fluid. And although the absolute concentration of these elements in both the brine and in the vapor-rich inclusions are different than seawater, their ratios is very similar to seawater ratios, regardless the brine or vapor state, which suggests that the contribution of magmatic fluid into the geothermal fluid at this depth is likely to be minimal. Otherwise, these volatile ratios would be very different in these fluid inclusions. Now let's take a look at a little bit the silicate melt inclusions. Their bulk composition lined up here is very similar to the bulk composition of the quartz-rich felsic veins which have been presented by Robert. The only difference is the sodium-potassium ratio. You can see that the quartz-rich veins are sodic, whereas our melt inclusions are potassic. Some of the melt inclusions also contain in the bubble phase an iron potassium chloride, very similar to what we saw in the fluid inclusion. So this suggests that the silicate melt is likely to have reacted with the potassium and iron-rich brine. Do we have any more evidence for this reaction between the silicate melt and the brine at depths? I think we do. We have analyzed uranium and thorium content of melt inclusions and fluid inclusions by laser ablation ICP-MS. The green dot indicates the composition of the silicate melt, and the red dots indicate the composition of the brine. You can see that the silicate melts have a very low uranium-thorium ratio and very high thorium content, whereas most of the brines have very low thorium contents, as thorium is immobile in brine, and very high uranium-thorium ratios because uranium is mobile in brine fluids. Most fluid inclusions are falling within this narrow range, but there are some fluid inclusions which petrographically look exactly the same as the others, but they contain higher thorium content than normal brine inclusions, which suggests that these fluid inclusions might contain a tiny bit of silicate melt. So what can we conclude based on all these? The temperature of the geothermal fluid at the bottom of the borehole is likely to be 600 plus minus 20 degrees Celsius, and the estimated pressure is approximately 45 megapascals. In these conditions, the fluid is not a single supercritical fluid, but it is separated to an H2O-rich vapor phase and a potassium and iron-rich brine. The H2O-rich vapor phase has metal contents very similar to the geothermal fluid sampled at shallower part of the Reykjanes geothermal system, whereas the brine is significantly enriched in noble and base metals compared to this. And they are actually very similar in composition to brines which are recovered for porphyric copper and molybdenum ore deposits. This means that the IDDP borehole didn't only sample high energy steam, but also an ore forming brine. The potassic character of the silicate melt inclusions at the bottom of the borehole is the result of brine-felsic melt interaction, which shows that the Reykjanes geothermal system at 4,500 meters depth is a dynamic system where silicate melt and geothermal fluid are communicating with each other. Thank you for your attention.
Okay, so hello everyone. I am Benoît Gibert from the University of Montpellier, and I will present you some data, some petrophysical data that have been acquired on IDDP2 course samples. We have, it is a work that have been done at the laboratory, Geoscience Laboratory in Montpellier. And we thank Robert and Gudmundur for providing the samples. Very, very interesting samples. So, the key questions related to this study are the following. So what are the in situ porosity, fluctuation degree, and permeability? What is the effect of temperature and pressure on rock properties during processes? And also what large-scale geophysics is telling us about small-scale process. And finally, are supercritical fluids detectable from the surface? So we worked on 13 core samples from 3,600 meters to the 4,600 meters. And our samples from rock physicist point of view are samples that are composed mostly of petroclays and calcium amphibole, that is hornblende. At more than 80% of the rock are composed of these two minerals. It means that these two minerals will probably control the rock physical properties. We have measured the porosity of each samples, and it is it goes from 0.5 to almost 3%. And what we observed on syntections is that the rocks are cross-cut by large fissures, fractures that are shown here by the arrows. And we have also intra and intergranular cracks. So first we have investigated the electrical properties at room temperature. So we have drilled cores, mini cores in the main cores. And the electrical conductivity is very interesting for characterizing the pore space. And the conductivity is equal to the conductivity of the fluid divided by the formation factor, F. And there's a second contribution at room temperature is interface conductivity. It means the conductivity that is allowed by charges located at the fluid rock, the fluid mineral interfaces. So by measuring the electrical conductivity of the rocks with different fluid composition and fluid conductivity, we are able to determine the formation factor and interface conductivity. So the formation factor is plotted here as a function of the porosity. And what we observed in general is that the formation factor increases when the porosity decreases. This is the case for the P29 sample. And we have observed two main trends, the two samples here in green and in orange. In green, the green samples are the samples that are located at the bottom of the well, while the orange one are located at the top of the core section. And the formation factor is very different. It is very low at the bottom of the well and is higher at the top of the well. It means that the pore space is completely different between these two kind of samples. And we have compared also our samples here in black with samples from the ODP, high ODP hole 1256D from a study by Marie-Violet et al. In 2010. And these samples are samples from a schistodike complex that have been altered in a chlorite amphibole facies. So very similar samples than ours. And what we can see is that the formation factor is really high compared to our samples. It means that contribution of the fluid in the conductivity is lower and the pore space is more complicated, I would say. Then I have plotted here the cementation index as a function of the porosity. What is the formation index? It is the index that relies the porosity to the formation factor. And when the cementation index is close to 1, it means that we have a porosity of fissural type, and it means that the tortuosity of the pore space is minimal. So we have, for most of our samples, a very low cementation index, and what we see is that the orange samples at the top of the well have higher cementation index, as well as the samples from IODP origin. And finally, we have determined the interface conductivity. And here the interface conductivity is plotted on a third diagram at the function of the porosity. And what we see is that the interface conductivity is quite similar to the conductivity observed in a high ODPU well, 1256. And it means that the interface conductivity contributes does not contribute to a lot to the conductivity of the rock. It means that the pore fluid dominates the conduction. So what we have seen is that the IDDP2 samples are strongly affected by fissures, open fissures that have been probably been generated during decompaction and thermal cracking because of temperature variation during drilling processes. So what we did then is that we measure the electrical properties as a function of pressure at high temperature, high pressure. So now the conductivity is a function of temperature, pressure. The conductivity of the fluids varies, the formation factor varies, the interface conductivity will vary with temperature and pressure, and with temperature and pressure we will have a contribution of the minerals that are considered insulators at room temperature, but that can conduct current at high temperature. So we measured first the electrical conductivity of the samples, of one sample PP2 that is located at the bottom of the well, and we measured it in a high temperature, high pressure vessel at a laboratory, Geosciences Montpellier. If we have a look on the electrical conductivity as a function of confining pressure, we can see that electrical conductivity decreases a lot with the confining pressure, which means that we observe a strong crack closure at depth, and the first cracks to close are the fissures that have been opened during drilling processes. Then we have investigated the electrical properties at high temperature, high pressure, high temperature and high pressure in two different conditions. The first one is in dry conditions. So the samples is heated and is not saturated with brine. So what we observe here on this diagram, where you can see the log of the electrical conductivity as a function of the reversal temperature, reciprocal temperature is here, and the temperature is here at the top. And the red points indicate the variation of electrical conductivity with temperature. The electrical conductivity increases linearly with temperature. It means that we observe an Arrhenian behavior, and when we compare this data to other experiments on blend plagioclase aggregate, we concluded that the iron Mg minerals contributes a lot to electrical conductivity. Then we have measured the electrical conductivity on a seawater saturated samples, PP2. This is always the same samples located at the bottom of the well. And we have measured it at a confining pressure of more than 1,000 bars and a pore fluid pressure of 350 bars or 35 MPa. So in the conditions that are very close to the bottom of the well, so in situ conditions. So what we observe is that the electrical conductivity of the saturated samples is nearly constant up to 300-400 degrees, and then it decreases, it starts to decrease at near the supercritical conditions, and it really increases at supercritical conditions. It means that the electrical conductivity now is explained mostly by the water conductivity, up to 400 degrees at least. And when we compare these experiments on magnetotelluric surveys at 5 kilometer depth in Reykjanes, this is values from the MT survey as are indicated here in red, one can observe that dry rocks cannot explain electrical conductivity at depth. So it means that the fluids even under supercritical conditions, have an electrical signature. And the physical origin of the conduction under this condition are still debated, as measuring electrical conductivity at a temperature higher than supercritical conditions is very difficult. Then we have investigated the acoustic properties at room temperature and then at high pressure. So we have measured the P waves velocities and the S wave velocities on all these samples. And we plot these velocities as a function of porosity. And we measured these velocities on wet samples, saturated samples with a fluid of seawater composition. So these are the blue points. And we have measured these samples under dry conditions. These are the red points. What we observe is that we have a big difference between the measurements done under saturated and dry conditions. In dry conditions, the measurements are lower than saturated conditions. And for this very low porosity, it means that we have a strong effect of cracks on acoustic properties. Once again, here we can see a big difference between the samples located at the top of the section and the samples here in green located at the bottom of the section. These samples are highly fluctuated, and we can see that the velocity, particularly P wave velocity, are very low. We have the same trend for the S wave velocities. There we observe a big difference. And finally, we have a relatively good agreement between the samples from IUDP 1256D hole and our samples in saturated conditions, here for the VS and here for the VP. So then we have decided to measure the acoustic properties at high pressure, as pressure will have a strong effect of crack closure, as we saw on electrical properties. So we measure the S wave velocities and P wave velocities as a function of effective pressure under dry conditions. And what we observe is that we have a strong variation of acoustic properties at low pressure between 0 and about 1000 bars. And this variation increases, exists up to 3000 bars or 300 MPa. It means that cracks are closing over the whole pressure range. The crack closure is very important at low pressure, but it subsists at high pressure. You can see it on the VP and also on VS. For these samples, we have calculated the velocity of the matrix because we know the elastic constant of the minerals, we know the minerals content, so we can calculate the theoretical elastic properties of the rock when considering that the porosity is known. So what we observe is that we have a big difference between the theoretical, the rock matrix properties and the real rock. This difference is attributed to crack porosity. And this difference persists up to 3000 bars. From this experiment, we have calculated the crack density as a function of the effective pressure, and we can see that we have a really high crack density, and this crack density decreases as a function of pressure. So we can see that cracks remain open at high pressure, in particular at in situ pressure around 1000 bars, 100 MPa. And then we have compared our results to geophysical survey. So there was a big survey during the IMAGE, European project IMAGE by Jousset et al. And it has been at about 5 kilometer depths, velocities of 5,400 meters per second were observed. This velocity is slightly higher than our velocities, and it corresponds to a crack density of 0.3. But this velocity is always lower than solid velocities. It means that at in situ conditions, cracks are open. And this is a very important observation. So finally, we have measured the permeability, not on IDDP2 samples, but on other samples from Reykjanes for another hole, N19. That was a dolerite of very similar composition, quite fresher dolerite than the IDDP2 samples. And we have measured the permeability under high temperature, high pressure using the same apparatus. And we can see that here on this graph, we have the permeability in 10 to the minus 19 square meter as a function of temperature. And what we observe is that when we increase the temperature here from ambient conditions to 200 degrees, the permeability decreases. And then between 200 and 400 degrees, there a very important increase of the permeability, almost 3 orders of magnitude. This increase is due to thermal cracking, and this thermal cracking is produced on a very narrow range of temperature. About 1,000 degrees of temperature variations are enough to increase the permeability by 2 or 3 orders of magnitude. So this is a very important result to explain the permeability at depth and also the crack generation at depth. So finally, to conclude, the IDDP2 core samples are highly fluctuated, mostly because of coring drilling operations. Electrical and acoustic measurements indicate that supercritical fluids in doré cracked rock have a geophysical signature. The fluids presence are indicated by the electrical conductivity, while the crack presence are indicated by seismic survey. So there's these two geophysical methods are very complementary for investigating the deep geothermal reservoir and supercritical conditions. So petrophysics and geophysics indicate that open microfractures and fluids are present at depth. And thermal fluctuation is probably the major effect that leads to fluctuation and in situ permeability increase. So thanks a lot. And thank you to Omar and Robert for providing the samples.
Okay, hello everyone. My name is Egil. I'm a geophysicist at Iceland GeoSurvey, and I'm going to give you a very short overview of seismic activity on Reykjanes, both prior to and during the IDDP2 drilling. And you see here the list of my co-authors on this project. So we will start with this map showing the seismic monitoring network deployed around the Reykjanes geothermal field during the IDDP2 drilling and stimulation. The red triangles are the permanent stations operated by ISOR for HS Orca since early 2013, focusing on the Reykjanes geothermal field. In green color are stations from the regional seismic network in Iceland, operated by the Meteorological Office, and they were a part of this online monitoring network. Then, in addition to the permanent seismic network, 9 temporary stations were installed within the framework of the DEEPEGS project. 5 stations were provided by InvestEUresearch and 4 by the Karlsruhe Institute of Technology. These stations monitored continuously but recorded offline, and they were installed to provide better resolution with regards to the possibly induced seismicity around the ITTP2 well. So now let's start by looking at the seismic activity in Reykjanes prior to the drilling of ITTP2 in 1 kilometer thick depth slices going from the surface down to 6 kilometers depth. And as we can see, the earthquake activity in the uppermost 2 kilometers in Reykjanes, or mainly at the reservoir depths, is concentrated below the production field and is most likely associated with the geothermal activity and production. Between 2 and 3 kilometers depth, we start to see induced seismicity in wells 33 and 34, and also the top of an earthquake swarm that occurred southeast of Reykjanes in October 2013. When we go deeper, we notice that below 3 kilometers depth, earthquake activity in Reykjanes is more or less located outside the production field. We see further evidence of the induced seismicity in wells 33 and 34, and also the October 2013 earthquake swarm southeast of Reykjanes. We also see signs of natural earthquake activity both below Skálafell and out on the Reykjanes Ridge. But my main emphasis here is on the seismic body that was discovered below 3 kilometers depth beneath the central core of the production field in Reykjanes. This seismic body coincides roughly with the same area that was rich in microseismic events in the uppermost 2 kilometers, or at the reservoir depth where the main production takes place. And this was an important observation because the ITTP2 well was to be drilled right into the center of this seismic body. As you can see, this is the well path of the ITTP2. Okay, so to summarize what we knew about seismic activity in Reykjanes prior to the ITTP2 drilling, then around 5,000 earthquakes were located during that period. The majority of earthquakes below the production field were small or below 2 in magnitude, while larger earthquakes tend to occur outside the production field. And as I mentioned, stimulation and injection induced seismicity mainly in well 34, but also in well 33. The depth of those earthquakes confirmed earlier observations that the brittle ductile boundary below Reykjanes is generally at 5.5 to 6 kilometers depth. But the most important thing was the seismic body evident below 3 kilometers depth. The seismic body coincided with a low resistivity zone within the high resistivity core below the production field in Reykjanes, as shown on the figure to the right. And in 2015, 3 hypotheses were put forward to explain this seismic body. The first one was that the lack of earthquakes is just a coincidence, as seismic activity in Reykjanes is episodic. But this was thought of as a highly unlikely explanation, as there is no evidence of seismic activity within this presently seismic body in the past. The second hypothesis was that the lowering of the pressure in the production field has reduced pore pressure at depth, resulting in increased rock strength. And this was thought of as a possible explanation because we know that production from the Reykjanes field is reflected by considerable subsidence, as seen in GPS and InSAR measurements. The third one was that the temperature is high enough within this seismic body to prevent stress accumulation to result in faulting. That is to say that the brittle ductile boundary is at close to 3 kilometers depth below the production field. And this was also thought of as a possible explanation. So let's now have a look at the seismic activity from the start of the ITDP2 drilling to the end of the main stimulation phase, or from August 2016 to September 2017. During this period, over 2,300 earthquakes occurred in and around the Reykjanes geothermal field, and all earthquakes have been manually picked and relatively relocated. And interestingly, seismicity was induced within the eastern part of the previously postulated aseismic body. Increasing circulation losses below 3 kilometers depth in the ITDP2 well, and the total loss of circulation from around 3.2 kilometers depth indicate the high permeability at this depth. And the most prominent permeable zone is found at around 3,350 meters depth, and most likely reflects a major fracture zone into which most of the injected fluid disappears. And all induced seismicity occurs just below the total loss of circulation, or essentially from 3.5 down to 5.6 kilometers depth. So during the almost 6 months of drilling, ITDP2 induced seismicity was more or less scattered and ongoing below 3.5 kilometers depth, with no large induced swarms, as can be seen on this figure to the bottom right. The average injection rate during this period was estimated to be almost 30 liters per second. Then, after drilling and as part of the well completion, injection tests were performed from the 20th of January to the 23rd of January after drilling to the final depth was completed. This is shown on the upper figure to the left. And no specific earthquake activity followed the injection tests. Then stimulation efforts in the ITDP2 well were carried out from February until July 2017. And this is shown on the lower figure to the left. And on average, 10 to 15 liters per second were injected from February until the middle of May, during which time induced seismicity was scattered and ongoing. Then a stronger stimulation effort started on the 16th of May, when pumping with rig pump started and lasted until the 19th of June. During this stronger stimulation effort, induced seismicity was, as before, scattered and ongoing. And finally, these efforts were followed by an intense stimulation from the 20th of June until the 28th of June. And induced seismicity was actually highest following the intense stimulation, or from the 30th of June until the 4th of July, with on average a daily rate of 13 earthquakes, including the largest swarm of 20 earthquakes per day on the 4th of July, which concluded with a magnitude 2.5 earthquake. So now to conclude, around 500 induced earthquakes were located deeper than 3 kilometers from the start of the ITDP2 drilling to the end of stimulation. The induced earthquakes are shown in green color on the figure, together with the ITDP2 well path in black and the main fracture zones as red circles. The earthquakes are predominantly small, occurring just below the total loss of circulation, or from 3.5 down to 5.6 kilometers depth. A p-value estimate is around 1.2, signifying the dominance of microseismicity. The induced seismicity seems to group into 2 different fault zones, a northern one from roughly 3.5 to 4.7 kilometers depth, and a southern deeper one striking northwest-southeast, which seems to delineate a fault going from the bottom of the well to southeast. Focal mechanisms of the induced seismicity show mainly strike-slip displacements, either right lateral or northwest trending planes or left lateral or northeast trending planes. This northwest-southeast trend, evident in the induced seismicity, is also evident in resistivity data and in the tectonic model of the Reykjanes geothermal field. This might suggest that the more probable plane of motion is northwest in the deeper part of the Reykjanes reservoir. And finally, a likely explanation for the induced seismicity is that the total loss of circulation of cold water into this previously aseismic body during drilling and stimulation has increased the strain rate sufficiently to make the volume seismically active. Consequently, the temperature of the previously aseismic body is almost at the brittle ductile boundary for normal strain rates. And that is all. Thank you.
So my name is Gunnar Þorgilsson from Iceland Geosurvey, or ISOR, and I'm going to talk about tracking fluid flow between the ITDP2 and the production field. And conventionally, this would be done by injecting some tracer material and measuring it in nearby wells. But due to the high temperatures around ITDP2, this is rather challenging. But during drilling, it was observed that the chemical composition in nearby wells changed rather dramatically, and especially in well RN12. And we assume that this is due to the injection of drilling fluid into the ITDP2 well during the drilling of it. And we want to try to use this drilling fluid as our tracer element. And here we can see the amount of chloride in well RN12 in the upper figure. And in the lower figure, we can see the drilling fluid flow rate into the ITDP2. And as you can see here, the drop in the chloride strength below the background level coincides rather nicely with the fluid rate that was injected into the ITDP2 during drilling. And well, RN12, you can see it here on the left figure, is here in the middle. And this is the well track of the ITDP2 well. And here on the right figure, we can see the well tracks of both wells. RN12 is a straight well, and ITDP2, you can see it here in red. And for our interpretation of the tracer or our modeling, we assume that there is one flow channel that connects these two wells. And the flow in this channel, we assume that is a simple 1D dispersion convection flow, which is described with this equation here. And you can see kind of the schematics of this setup here on the right figure. And this is a standard method to interpret results from tracer testing. But we are not in standard situations, so we have to do a little extension of this model. And the first extension that we have to do, and maybe the more critical one, is that usually the tracer injection is instantaneous. But as you can see here on the right figure, the drilling fluid, which we are kind of using as our tracer, is not instantaneous. It extends over several months. So we had to take the solution for the instantaneous injection and integrate it by time. But we got a closed analytical form that was nice to use. But I will not bore you with the equation itself. And the second extension that we had to do to the standard method was that usually we are measuring the excess of tracer material. But in our situation, we are actually measuring the shortage of tracer material, which is chloride concentration in well RN12. And we calibrate our model to the measured data points. And as you can see here on the figure on the right, our model is shown with a blue line, and the measured data points are in orange and purple. And as you can see, our model fits rather nicely to the measured data points. And also in the inset figure, we can see when the injection started, or the injection of the drilling fluid started, and when it ended. And from this calibrated model, we can get quantitative results, for example, as the effective flow area that the model gives of the flow area of the channel, as well as the average fluid velocity and the rate of how dispersed the flow is, and also how much of the injected fluid, drilling fluid, is going into the channel. Well, so this result from the flow model can be used to make a very simple heat model. And for example, we can use this heat model to predict the change in temperature in well RN12, for example, if we would inject cold fluid into the ITDB2. And we get most of the parameters that we need. The only parameter that we don't get from the calibrated flow model is the width and height ratio of our flow channel. And we assume for our heat model that we are just having this rectangular flow model, and the heat is flowing into the fluid by conduction. So we have to compensate for this by doing a pessimistic prediction and optimistic prediction. So here in my last slide, we have the result of the heat model or the temperature model. If we assume that we are injecting 100 kilos of 50 degrees centigrade warm water into the ITDB2, how the temperature in the production temperature from well RN12 will behave from start of injection and 40 years onward. So our most optimistic prediction is that it will actually stay rather stable, just dropping by 1 degree over the whole period. And then one more pessimistic prediction is that it drops by more than 25 degrees. Well, so this was my presentation, and I would like to thank you for your attention.
So, good morning. I'll be talking about some geochemical calculations that we carried out in order to try and estimate the possible chemical composition of the fluids that we might get from well ITDB2 during the flow test that was planned. And initially this was done for the flow line design group to aid them in the selection of materials for the flow line. So the well has 3 feed zones at approximately 2.3, 3.4, and 4.5 kilometers depth. And estimated injectivity indices suggest that about 95% of the discharge will come from the largest aquifer at 3.4 kilometers, whereas only about 5% or around 5% will come from the deepest aquifer at 4.5 kilometers. So in order to estimate what type of fluid or what the composition of the fluid we would get when the well discharges, we use these predictions and these mixing ratios to find out or to estimate this. So we attempted to model the mixing of fluids from these 2 lower feed zones and how that mixture would evolve as it ascends to the surface. And In order to calculate the composition of a mixture, we must, of course, first know the composition of each end member. And from the estimated temperature and pressure of the feed zones, it seems that the fluid that we find at 3.4 kilometers would be a single fluid or single liquid, similar to what we find in the present production wells at Reykjanes, which are shown in the yellow or the orange field here, except only hotter and with under higher pressure. Whereas the fluid at 4.5 kilometers depth was expected to be a two-phase supercritical fluid with a dilute sort of vapor-like phase and a hypersaline brine phase. And well, I don't see, oh, I can see it here. And I should add that this estimate here, based on the well logs and Horner plots, is significantly lower both in enthalpy and pressure than what Eniko Bali just presented to us, which would fit somewhere about here. But nonetheless, we expect to find a two liquid mixture. So we assume that the deeper liquid starts at 4.5 kilometers and then boils adiabatically on its way up the well bore. But when it hits the larger fluid mass at 3.4 kilometers depth, it will be more or less quenched. And we assume that it will form a single liquid mixture at 3.4 kilometers at approximately 350 degrees. And after calculating what that mixture would look like, we simulate boiling of the mixed fluids to a pressure of 70 bars, which was the estimated wellhead pressure during discharge. Use this to assess the most important chemical parameters of the fluid. And for this, we used geochemical modeling software, Watch, and Kim and Solveig, which all work up to 350 degrees, but not at higher temperatures. Let's see. Yeah, whoosh, too much. Aha. So we assume, as I said, that the fluid at 3.4 kilometers depth is similar to the conventional Reykjanes fluid, only hotter. So the straightforward way of simulating that is to take a typical well sample from Reykjanes and heat it up to 350 degrees. And as we know, particularly from the work of Vigdís Harðardóttir and others, that the fluid sampled at the wellhead has already lost some metals due to sulfide precipitation during boiling. In the reconstructioning of the fluid, we allowed the fluid to equilibrate with the relevant sulfides, galena, sphalerite, chalcopyrite, and others, as well as rock during the reconstruction and the stepwise heating to 350 degrees. The fluid at 4.5 kilometers depth is more difficult to model, but our best guess at the time was to estimate its composition using fluids that have been sampled from black smokers on mid-ocean ridges. However, although many vents have been sampled, none of them really approach the estimated temperature of the aquifer at 4.5 kilometers, nor do they show salinities close to the extremely high salinity that Eniko Bali and others have suggested from or found in the fluid inclusions. But we chose two samples from the same vent at the East Pacific Rise. One which seems to be that it could represent a dilute phase, and one that is more saline with lower H2S. And so on. And based on the samples, we calculated the composition of both these phases as single liquids at 350 degrees. So then we had two fluids at 350 degrees, and the next step would be to calculate how these fluids mix. So we calculated 4 different mixtures using the Reykjanes fluid as the main constituent, or the hot Reykjanes fluid, as 90 or 95%, and added to that 5 and 10% of the dilute phase from the black smoker on one hand, and the brine phase on the other hand. And the table here shows the composition of the mixed fluids, and I won't go into details there, but at least we see that the fluid composition is dominated by the conventional Reykjanes fluid, as expected. The in situ pH is close to 5, and the salinity is similar to seawater. The main effects of the deeper fluids that we see is higher H2S for the mixtures containing the dilute phase, and higher iron and magnesium for the manganese for the brine mixtures. So once we have the mixtures, we can allow them to boil to 70 bars. And after boiling to 70 bars, this mixture, which now has a vapor fraction of about 25%, so it's two-phase, and the vapor phase has relatively low gas content, about 0.7%, whereas the liquid phase has pH close to 4 and a fairly manageable composition. And during this boiling, we see some precipitation of solids, around 10 to 20 milligrams per kilo of fluid. But we see also from the concentration of iron and other metals and H2S that the resulting liquid phase still has significant potential for sulfide deposition when it boils further. And we should note that in the conventional Reykjanes fluids, there is significant sulfide deposition when it boils from about 40 bars to about 20 bars. So to explore that further, we simulated boiling down to 19 bar, which is the turbine pressure at Reykjanes, and found, as we expected, that even though there's some precipitation at the beginning of boiling, we get another precipitation phase that starts at around 45 bars, precipitating mainly sulfides, about 10 to 30 milligrams per kilo. And then at about 30 bar pressure, we start to see amorphous silica precipitation as well. And the total amount of precipitates for the fluid is calculated to be as high as 70 milligrams per kilo. So that is, which is considerable. Yeah. So to conclude, these predictions, with all the limitations that we should keep in mind, suggest that at 70 bars, the fluid should be quite manageable and probably further down to about 45 bars. But further boiling would result in substantial deposition of solids. So if we were to go further down in pressure, we would have to either find some way to counter that, or it might fill the well with time. And that was really it. Thank you.
Good morning, everybody. My name is Þorleikur Jóhannesson, and I am going to present a few slides about the wellhead and flow line design for the IDTP2 well at Reykjanes. We did this in cooperation with HS Orka, Mr. Albert Albertsson, and Geir Þórólfsson, the chief engineer, and also with Ásbjörn Einarsson, our material expert. So if we start with I will start with a short introduction, followed by some very important things about design premises. I will show you how we put together the piping and instrumentation for this wellhead and the flow line. Few words about the master valve and also the special made modulation orifice valve, which has been in use at HS Orka for many years now, but we did some modification on. Instead of having nozzles on the flow line, we decided to have spools. I will show you some slides of that. A little bit about material selection and cladding. Vibration problems they observed in IDTP1 and how that was how the experience was brought into this design, and then I have few slides of the installation. Designing such a surface equipment to receive and cope with super hot geothermal fluid can be quite challenging. The aim of drilling of IDTP2 at Reykjanes was in the beginning to reach 500 degrees centigrade and 300 bar. And this requires a design premises for pressure and temperature at the wellhead in the range of 250 bar and 475 degrees centigrade respectively. This provides a challenge for as very few equipment providers are dealing with valves and items that can actually cope and are designed for this high pressure rating. The chemistry prediction was also quite challenging, but Finnbogi Óskarsson showed us in detail what that was all about in the previous presentation. Furthermore, mechanical issues, fluid structure interaction, and so on, vibration were also issues for concern. In cooperation, as I said, with HS Orka, Verki started this design prior to drilling of the well some years ago. And after the drilling of the well, the design premises changed. But however, we decided to use some of the work we did earlier. So many of the ingredients of the wellhead are actually designed to cope with higher pressure and temperature than IDTP2 showed at the end of drilling. So this is actually just a cross section of the well. You probably all know about that. That was not included because there was another design group that they did take care of the design of the well, and their design actually ended, so to speak, at the expansion spool here and the IDTP2 refurbished IDTP1 wellhead valve. So, as you probably know, what the actual values for IDTP1 well was so that the temperature at the wellhead was observed up to 450 degrees and pressure around 150 bar. And we see this point where the blue dot on the pressure temperature diagram for this material 1.9 is located. So you can see that actually the actual the actual outcome of ITTP1 was actually below class 1500. What we expected for the, before drilling of ITTP2, we expected situation close to where the red dot is here, almost up to 500 degrees and 250 bar, and just on the edge of what we know of as the class 2500 for this material group 1.9 according to 16.5. But then after drilling of ITTP2, it turned out to be a somewhat colder and lower in pressure, as Finnbogi also mentioned on the slides before, temperature up to 350, pressure 120 bar, and as Finnbogi mentioned, where part of majority of the flow came from the permeable zone at 3,400. And then we estimated that the maximum enthalpy would probably be close to 2,000 kilojoule per kilogram. So this is a little bit less than we expected, but nevertheless, we decided to design the wellhead upstream of the orifice according to class 2,500. So this is just a cross-section of the master valve. It's a TEEPEGS 1500 valve with 2,500 flanges. It is the same valve they used in ITTP1, but this was brought to this program as well. And ACES Orca, they did a modification where they put some extra cladding on the ceiling surfaces and so on. So it is, and they have, of course, replaced the broken stem or the broken shaft for a new and more sophisticated material than was previous. So I think this valve now is at least much better than the valve as it was bought from TEEPEGS before the drilling of the ITTP1 well. So it was actually reused. So we decided to design all the flanges and spoolers at the wellhead to class 2,500. The master valve, as I said, is a 1,500 class valve with 2,500 class flanges, and all other valves on the wellhead, 1 to 4 inch valve, they are all in class 500 and all with this ASME 16.5 material group 1.9. And the wellhead is completely on all the wet surfaces because of the chemistry of the fluid. It is cladded with Inconel 625, all wet surfaces, and the RTJ grooves on the flanges as well. And actually we can say on the wellhead itself there are no pipes, there are only valves and spools, and I will show you a picture of that a little bit later. The flow line, as you heard Finnbogi was telling before, we wanted to be able to keep the pressure, you know, almost over the entire range of what we could expect. So we decided to design the flow line itself of class 900. And you can see here that the flow line itself is 250 millimeter and it is in 16 millimeter wall thickness. So it is quite sturdy and heavy flow line as well. So we can actually keep the flow line under, you know, 100 bar all the way up to the muffler. And we thought that would be essential because we actually did not know exactly what would come up there. So this is the piping and instrumentation diagram. You see here is the well. There are all sorts of sensors and cameras and so on because there was we took this through health and safety design and all sorts of things. We wanted to watch it from other locations. Here you see the spool piece where we can divert the flow to the secondary flow line where we have a muffler, and then through the orifice valve to the atmospheric separator. And as you heard, because we expected now this was not going to be superheated or supercritical steam that we got to the surface, but more of a saturated steam here. So we decided to use the atmospheric separator to separate the water from the steam. On the flow line, there are a lot of instrumentation. There are orifice flow meters, and we have all sorts of tapping and so on. And here you see this special HS Orca valve. And then we have the secondary flow line to the muffler. This is, here you see just a picture of the wellhead. Here you see the class 2500 valve, and here underneath is the expansion spool. So we expected vibrations from the valve, so we decided to build a very sturdy concrete supports around the wellhead, and we have this very heavy and sturdy stiffening bars, and we expect the well to rise several millimeters or even centimeters up, so we have a room for that as well, and that has been taken into consideration as well. This is the special orifice valve. The flow is actually coming here from the bottom and through here. You see, this is actually like an orifice, and there is a plug or a stem here, and this is the shaft, and it is hydraulically activated. Inside this valve, it is fully cladded with Inconel 625, and on the surfaces where we expect erosion, we have a stellite overlay. HS Orca, this is their innovation. It originates since Svartsengi. Then they produce it as a class 600 valve. In Reykjanes, we have a lot of class 900 valves, but this is actually a modification of the class 900 valve from Reykjanes with all this well done and overlays and so on, and the new material or very sophisticated material in the stem as well. So this is actually a homemade modulating orifice valve to control the flow from this well, as they do for other. As I said, it is a class 900. This is a class 900 valve. The main body is produced of 16 MO3, and the flanges of some relatively similar material. It is cladded with Inconel, and shaft and cladding on the stem is stellite and so on to cope with erosion. Here you see what we, in ITTP1, you see this is the wellhead there, and you see there are these nozzles that are actually welded on the pipe coming from the flange here and up here. And this is something they had some mishaps here because they broke because of the vibration, and for ITTP2 we decided to not to use any sorts of pipes or nozzles, and instead we produced of a solid block of steel class 2500 diverter. You see the flow is actually coming up here, and then we have a same size side outlet, and then we have some other smaller outlet for all kinds of instrumentation and for the secondary flow line. This piece is cladded with Inconel 625 on all wet surfaces, and you see that the connections, they are bolted with stud bolts right into this, and we made the RTJ grooves here and cladded with Inconel and so on. So everything is done as, as sturdy as possible. So this is how the well head actually look like. You see here is the expansion spool. This is the master valve. We have here this big spool we specially made, and this is the side valve, and here you see the orifice valve. And you see all tappings are done with valves that are bolted directly to the spools, so there are no actually nozzles or pipes in this design. All valves bigger than 1 inch are hydraulically actuated. So on the flow line, we needed some information, or we we needed to have some tappings, both for testing and for some pressure measurements. And instead of welding nozzles to the flow line itself, we decided to clamps. We call it a measuring spool, so we can rotate it any way we like to do. You know, so the guys who want to take samples, they can actually select between 1 inch and 2 inch, and they can select to come with their tapping under or on top or to the sides. So this is the same. We needed to measure the flow. We produced a special orifice spool, so it is not a simple orifice that is clamped between flanges. It is already made with all the tappings bolted directly to the orifice spool. One problem they observed in ITTB1 was that the bolts, you know, bolting the flange for valves to the lower valve or the expansion spool, they became loose. And they thought in the beginning it was mainly because of some vibration. And if you look carefully, you see that they have welded some metal straps here around to prevent the bolts from getting loose. This is what they had to do in an emergency situation, and there was actually, you know, but it's obviously not the best way to overcome this problem. And it was we discussed it a lot, how this could happen. And we think actually it is because of the RTJ ring. It is very important when you have this RTJ flange connection that the ring is softer than the flange itself. And another thing that is more important is that the thermal coefficient of the steel, of the ring and the flange, they must be similar. All the rings, the RTJ rings in ITTB1, they were of 316L, which has a thermal coefficient, expansion coefficient 50% higher than carbon steel. And we actually believe that this is the main reason why the bolt came loose, because I borrowed from the internet a very interesting filament element analysis. It is from James Walker since 2012. You can see that here you see the ring and the flanges, and here you have tightened the bolt up to almost up to yielding of the ring itself. And because when you heat it up, the thermal expansion of the ring is greater than the flanges, and that means that it will expand more and it will actually yield. And when it cools down again, then the deformation is so that the bolt has lost all its tension. We have not done finite element analysis of exactly ITTB2 connection, but we plan to do so in the coming years to see if this is actually, and you see this can be catastrophic if the bolt loses its tension. And then everything becomes loose and you get leakage. So this is probably not the best connection to have if the temperature gets so high, unless you are very careful when you select the material or material combination of the flange groove and the ring itself. We think it is very important. We also introduced some new, or not new type of washer, but washers that have not been used so much in geothermal that will actually secure the tension of the bolts during those hot heating and cooling cycles of these connections. So just a picture from ITTB2. Here you see in the beginning they had manual actuators. They changed to hydraulic, and all our actuators in ITTB2 are hydraulic. This is the atmospheric separator, and not so much to say about that because, as I said, it is going to be a wet wet fluid that is actually coming out of the well, so we can separate it. We can measure the steam flow up a chimney, and then we can measure the flow of fluid in a weigh box. This is how it looks like on drawing. We can have a Russell James nozzle here. We have the measuring of the steam velocity here, and so on, as I showed you before. This is simply a plan view of the separator. There are some diverters in it, and there are some chevrons to filter the steam from. But of course, as Finnbogi mentioned, when we actually go down to atmospheric pressure, we can actually expect a heavy buildup of deposits in the separator, and therefore it needs to be cleaned very regularly. We actually don't know the interval between cleaning, but we have the secondary flow line to use while we clean this. And this is how this separator looks like when it is in operation. This is on the secondary flow line, we use our invention of a special rock muffler, some experience we have gained and HS Orca through some steam blowing procedures of their turbine inlet pipes. Actually just simple concrete block, as you see, filled with heavy stones and so on, and then there are holes on the pipes. So this is the final setup. Here you see the wellhead itself. Here is the orifice valve, and this is actually the main flow line here towards the separator and the weigh box. And then we have the secondary flow line out of the nozzle spool here and to the rock muffler. This is how it looked like. We see here a closer look at this crossover or the special wellhead spools, where the flow comes from the bottom and then to the sides here and the valves are directly bolted with stud bolts to this piece of solid metal. Here is the separator, and here you see the sturdy platform around the wellhead to absorb any vibration or forces and so on. And this is actually picture taken some weeks ago from Guðmundur Ómar. You see, here they have put some raincoats over the main parts, and you hear there are a lot of small pipes here for the hydraulics of the actuator and so on. This is the secondary flow line, and this is the main flow line, and the flow is coming actually here and towards. We put on most of the bends we have T-junctions and then a blank flange, because the bends are not so good due to possible erosion. So this was all. I thank you very much for your attention.
Yes, thank you. My name is, as I said, Sturla Sæther from Equinor, and I have been working with IDDP2 from the beginning. And one big question in this well is, are we able to produce supercritical fluid from the very bottom? We have heard something now that we will not be able to do that for pure fluid from the bottom, maybe. So I will go into the investigation of how we have worked to find out more on this. So if I can come to the next slide. I can't see the pointer here. I cannot see the arrow. Thank you. So what we have been doing in IDDP2 is to do different injectivity indexes, injectivity tests to see what are really the injectivity of the different zones, and also the different times of of this well. And I have picked out some temperature measurements during injection of cold water into the well. And then we can see from these different yellow arrows that there are some interesting points, especially here at 2,300 meters. We have a point where we can see a small step in the temperature measurement. And this is an indication of a casing mostly collapse, or we have a damage of the casing in this zone. So we expect that in this zone we get some inflow from the reservoir into the well during these inactivity tests. And as we also have heard many times, that we see that at 3,400 it's a certain break of the temperature profile, and this indicates also a potential production zone. And for simplicity, so I have introduced a production zone down at 4,400, which let's say a gathering of the deepest part of the potential production zones. There are some, let's say, turns on the graph further down there, but to be able to do inactivity indexes calculations locally based on the overall inactivity number we get by the tests, I have introduced these three main zones. So it's one zone at 2,300, one zone at 3,400, and one zone at 4,400 meters depth. So now we'll try to go to the next slide. I cannot see the arrow. Yeah, thank you. So what we have assumed is the reservoir temperature, and we have a good understanding of the reservoir temperature from previous wells, let's say down to 2,500 meters. We have a steep increase in temperature, and then we have from about 1,000 meter down to close to 3,000 meter. It seems to be quite constant, and this means that we have a very good production zone. It's a lot of water circulating in this area. And what we have done further on is to do some predictions of the temperature further down to the deepest part. And in this assumption here, we have had some work been doing in Equinor by Ketil Hogstad, and it's also other people have been discussing this today. And the assumption in this work is that the temperature at the deepest part of the well is somewhat hotter than 500 degrees. So this is the temperature profile for the reservoir we have been using. And by having this temperature, we can also calculate a reservoir pressure. So I need some help to the next slide. So by doing this analysis, I have set up the violet line here is representing the reservoir pressure down to the deepest part, and in the deepest part here we have assumed the supercritical fluid, and then we have let's say a turn of the pressure profile. The blue line is the well pressure that we have been measuring during inactivity tests. And this blue line here is corrected and represents when we have no water injection into the well. So then we can say that we at 2,300, where we have defined a typical zone, we see that it's an overpressure from the reservoir to the well, and then we can expect some inflow here. At the deepest part, at 4,400, we see that it's a typical overpressure inside the well because of the cold water column. So it's also thinking that water from the well will flow to the reservoir in this location. At 3,400, it's a very small pressure difference. So it's uncertain where we have inflow or outflow, and if we have small water injection in this injectivity tests, we know for sure that this will also go water out in the formation. But when we have no feed of cold water, it seems that we have a very small overpressure in the reservoir in this location. So what we can say is that the balancing point of the well is close to 3,600, 3,700 meters for this case. And this is representing the inactivity test that is done the 3rd of January 2017. And at this day, the total inactivity index was 1.7 liters per second and bar. And by taking different flows and this total inactivity index, we can then distribute this total inactivity index to the different zones. And then I have found that at 2,300 meters, it's a very small inactivity index. At 3,400, it's quite big. It's 1.3 out of this 1.7. And at the deepest part, it's a small inactivity index, 0.35 liters per second and bar. And this means that the main production zones will be from 3,400. And then I should have changed to next. Thank you. So this graph here shows the 3 different inactivity tests that has been done. One is for 3rd of January 2017, and the total number is 1.7, as I just showed you. And this yellow representing the deepest part, 4,400. This red one represents 3,400, and you have a very, very small blue one at the bottom here that representing the damage zone. Between January 3rd and January 23rd, we did a lot of stimulation in IDDP2. And then we managed to raise the total inactivity index for the well to 3.1 at 23rd of January. And then I made the same calculation as previous showed, that the zone of 3,400 is the main contribution to the total inactivity index. We have also done later on inactivity index test at the 10th of September 2018, one and a half year later, and it seems that the total inactivity index this day was at 3.0, and still it's the main zone is 3,400. And to try to predict where we will get the flow from when we start the well, I have then stated that the local inactivity indexes for this well is for the 2,300 meters part, it's 0.05 liters per second on bar. 3,400, it's 2.7. And the lowermost part at 4,400, it's only 0.3 liters per second on bar. So the main contribution to the inactivity index is the 3,400 meter zone. And then I have used these zones to estimate the flow from different zones when we manage to start the well. So then I need the next slide. So by doing simulations of the well, we can state that if we see that we will manage to produce 30 kilograms per second from the well, that is representing by this red line here. So at the very bottom, it's a quite big pressure difference between the reservoir, which is this violet line. So it's a highly drawdown in the well at this part, but it's also at 3,400 in this part. It's also high drawdown, and the inactivity index here is quite high, and this means that you will get a high production from this point. So from the bottom up to 3,400, it's more or less the static pressure difference. And then you start to produce up to the uppermost part, and then you end up with a pressure at the wellhead about 85 bars in this case. And this is for 30 kilograms per second. If we say that we can open the valve even more and produce the maximum of the well, then we can be at this left border. But if we more or less close down the well and have a very small flow rate, then we will have the pressure at the top side. In this figure, 185 bars. So then the question is, when we adjust from full opening, full flow, down to more or less closing the well, will that make any big difference in the pressure conditions in this area and in the lowermost area, so that we relatively can produce different rates from the different production zones at 4,400 and 3,400. The zone at 2,300, the damaging zone, will not affect the well very much. It will lose some of the production in that region at high pressures. It will also lose relatively more when we have small flow rates, but it will not come any fluid into the well. And that's very important to analyze when we do this chemical analysis from the deepest part compared to the 3,400 part. So then to the next slide. So what I have plotted here is the production share from the different zones. So as we take, if we take this 30 kilograms per second, we see that we have close to 95% of the fluid is from 3,400. It's only 5% from 4,400, and the damage zone at 2,300 zone is very close to zero, so it will not affect the flow much. But when we reduce the total flow from 30 and go down to 5, and in this region here, we can see that the relatively flow from 3,400 is decreasing a lot. And then we start to produce relatively more from the deepest part. And even if the total flow is very small, we will get the relatively most of the fluid from the deepest part. And I think that's really interesting to recognize, and when we should do the measurements. And the main goal of IDDP2 is really to understand what is the chemical in the supercritical reservoirs, and then we should be aware of closing the well close to closing, and then we will produce most fluid from the deepest part. And I think that's concludes my work. Thank you.
Good afternoon, everyone, especially for those that are joining overseas. First off, I would like to thank everyone who's been involved in the project. I think it's been great. Okay, now I have the control, I think, so I can flip it. Yes, so my name is Guðjón. I'm the head of reservoir management at InvestEUresearch, and I will here present the ongoing process with the flow test of IDDP2. So, okay. So I'll kind of start with the summary, but the well is currently not flowing, and it hasn't flowed yet. The stimulation process started in December and has been ongoing since then to try to get the well flowing and to figure out what's the reason why it's causing us a little bit of trouble. We found an obstruction in the well in June last year at 690 meters depth. It was of an unknown source, and later when we tried to do another attempt now in March, when we thought the well might be more likely to be open, we found an obstruction at 780 meters roughly. But so this has caused us problems, but we've been fortunate enough to have fiber optic data in the field in cooperation with GFZ, with Martin and Thomas, and Martin will present further details about that later. But this has been very valuable to know about the changes that are occurring within the well in close to real time. And Martin has been really good to provide us with updates. So we've been monitoring the changes as we go along. And efforts are still ongoing to try to get the well flowing as soon as possible. So yeah. So here you can see an example of the data we've had from the fiber optic. From before we started the stimulation of flow process or efforts. The graph shows the changes for about 3 weeks from the 18th of October to the 11th of November. And in the beginning, we saw this distinctive kink in the temperature data, which we interpreted to be a plug or some sort of obstruction in the well. But as the days passed and weeks passed, we saw the temperature rise in the well. And if I, yeah, and later on, we saw the well kind of opening up. We saw a decrease in pressure. We saw a lot of steam admitted from the well and temperature rise close to the wellhead. So we could kind of see what was happening inside the well. But at the wellhead, we only saw steam come out in the beginning, a slight, like a breeze, pressureless steam, but later on we could see it was really emitting steam. So there was a buildup of pressure below this obstruction. Oh, wait. And as I said, the stimulation process started in mid-December when we started to inject cold air into the well to raise the wellhead pressure to about 40 bars, which was the limit of the pump we had. After we had raised the pressure, we'd leave it for a certain amount of time before releasing the pressure again. At first, we did that slowly, but later on, we increased in increments how rapidly we would release the pressure. And the figure here on the right shows the first pressure release from about 10:15 in the morning to about 1 o'clock in the afternoon. And you can see the kink in the pressure profile, which has been interpreted as the effect of the plug that we had and really lower impermeable plug before that was obstructing the flow from the well. But this we could see very early on did not continue. We saw the plug opening up and we saw the well heat up further. And it's worthwhile to note that the volume of air has always been higher than the volume above the obstruction. So this has made the conclusion it's at least permeable to air, but there is something getting through it. Oh wait, and here you can see all of the cycles that have been ongoing since December. We've done a number of cycles with different approaches to them, and with the time in between them different as well. The last pressure release was in mid-March, as you can see, and that was before we had InvestEUresearch come in and attempt to measure the well, and they found the obstruction. As I said before, we found this obstruction at 780 meters depth, and we were already monitoring from the fiber optic that something was happening at that depth. And I hope you can see my mouse where we saw a more rapid temperature change or anomaly occurring at this depth in close relation to the cycling of pressure on the well. So this we found really interesting. The source of this obstruction or what it is unknown, but something is at least transferring heat faster to the fiber optic at this depth. So, and this has been at this depth now for some time. And And here I had this is the newest temperature profile I had from before when I submitted the slides, but we've been looking at changes occurring now over time, and we see that this step has formed again when we leave the well alone, but we know of the obstruction further down, further below that, so the cause of it is of a different source. But we see that the well is really dynamic. It's constantly changing, and we've had to kind of learn as we go along as well what we can trust and what not. But we see the well now heating up. It has even heated up more than this. It's close to 80 degrees at the wellhead, according to the fiber optic. I think it's just at about 20 meters depth in the well. So there is heat coming up the well. It's moving along, yeah, I think I had on the last slide. The kind of next steps and what we're trying now to do is that we have kind of three scenarios. We have injection through the wellhead where we can inject hotter fluids around 80 degrees to try to put weight on the plug to see if it moves or see what happens. If we see cooling below, we know that fluids are getting through, or if we see that it's sealed the well. So that's kind of, I would say, first option. We could also bring drill on site to open up the well, and that's a possibility that needs to be looked into as well, but it's of course very costly and timely as well. And because of COVID, it's not helping with rig availability and so on. And the last is that we could wait for the well to open again. We see that it is heating up. We like to think we always see steam at the wellhead again, but it is unknown when this would happen and how long time this would take. But we see that it is constantly changing. So we could have a window that we could use at some point. But as we don't know what the cause of the obstruction, injection through the wellhead also gives us the opportunity to put a camera down at some point if we want to try to see better what we are dealing with. So that's kind of the current situation with the well. And the process is still ongoing to get the well flowing. So we will try to utilize the opportunities we have now, and sooner than later, hopefully have the well flowing. So I'd just like to thank everyone for attending and listening in.
Hello, everybody. So I would like to go a bit deeper into what Gudjon was just telling us about. So a bit about the real-time monitoring that we were performing in IDP with fiber optic cables. So I want to use my time here to give you a short overview about how distributed fiber optic sensing works, and also the field installation that we performed in 2016 in Iceland. Then I will also show you some field data that we collected, and then jump to the conclusions. So yeah, the motivation for us is absolutely that the well integrity is very fundamental, and especially in such a high temperature and pressure regime that we encounter there in Iceland in this IDP project. This is a huge challenge, and usually downhole data is very limited and requires well intervention, as we all know. So what we did is we used a fiber optic distributed sensing technology to install the fiber permanently into the wellbore, and by that monitoring different well operations in IDP2. To give you a short introduction of how this works with distributed sensing, if you want to use a glass fiber, you can basically bring it down to three components for most of the equipment which is out there. So you have a laser source that guides light into a glass fiber that can be many of tens of kilometers long, and the light is guided down through the fiber, and all along the path a certain portion of the light will be scattered in random direction, and the portion of this light is traveling back to the origin, to the source, where it can be detected then by a signal processing unit. So now you can do different things, and as Gudjon already showed us in the last talk, you can measure temperature with it, or you can also measure strain, and this is what I will also show you in this little example here, that you can also measure static strain changes of the glass fiber as well as dynamic strain changes, which is also known as technology as DAS, or distributed acoustic sensing. So the installation that we performed in 2016, that was together with it was actually within another project. It was the GeoWell project, also a Horizon 2020 project. And there you see here on this picture, first on the left side, we've seen this before, and on the right picture, the installation of the cables. So there was a control line installed with a couple of thermosensors and pressure gauge in combination with our fiber optic cable, which was then landed behind the 958, 978 production casing, which you see here on the right sketch, where we have a piece of around about 30 meters open hole section, and the rest is running in the casing and casing in the well. So as I said, the cable was installed in this project called GeoWell, and there from 2016 to 2018, we had different measurement campaigns, which was cement pumping and hydration, for example. That was the first bit after the cable installation, which we measured with a distributed temperature and distributed static strain changing. And then we also had a phase of fluid injection phase and shut-in and quiescence, which was in combination. We did this with a DTS and DAS unit. It's also TNO from the Netherlands was involved in there. And we made a little small vertical seismic profiling campaign with a new device there. Now within DeepEGS, we had the additional opportunity to monitor. There was actually data that Gudjon also already partly showed of the well bleeding and stimulation phase, which is still ongoing, at least with DTS until today. We also had a phase of DAS sensing, distributed acoustic sensing, and this data I'll show you briefly now here as well. So this data we've already seen, that was Gudjon was showing, this phase in October last year, where there was this apparent obstruction in the well, and then over the days there was this boiling point curve building up in the well, which then at one day collapsed, and then there was sort of a dynamic happening within the next days of this event. I would like to show you now a bit more about this collapsing phase on the next plot here. This is now you see again, this is what you see on the left plot here is a temperature curve just basically seconds or minutes before this collapse occurred. So there was just a moment where we had this profile, and next to it you see a 5-second distributed acoustic data snippet. So 5 seconds of noise recording here displayed in the frequency domain. So what this shows is that in the lower part where this obstruction was like thought to be, there's a bit of noise going on, as well as in the more shallower part at this top of this boiling point curve, there's some noise happening at this time, just qualitatively speaking. Now on the right, what you see is a temperature plot just 18 minutes after the left one. So this is just the ongoing kind of opening up of this obstruction, and this is what we are currently investigating, these sort of data here at GFZ. You see here this huge increase in noise in this data, that we have interesting frequency patterns in there, and we're now looking into like what kind of story we can make out of this sort of information of such a well. So this is just to show you something here on this plot. If you have any further questions, feel free to contact me. But for now, this is all I wanted to show at this point. And yeah, conclusions are pretty much intuitive. I think it was very great for us to be able to monitor so many different phases on such a thrilling project. And we'll also deeply again like to thank ESOR and HS Orca for making this possible for us. Every time we had to make so many logistical things of bringing things back from Germany into Iceland and back and forth, and without your help, this would not have been possible. And thanks also for the organizers and the rest of the committee.
My speech will be on monitoring the DPGS, the Reykjanes geothermal reservoir, with geophysical techniques and in particular electromagnetic techniques. So I just would like to say and thank the different authors of this paper, which are from BRGM, but also from ISOR, from KIT, and also thank InvestEUresearch for all the logistical help during the measurements. So what we did during this experiment within the frame of the DPGS project was to actually test the ability of electromagnetic techniques to monitor geothermal reservoirs, the development of geothermal reservoir. And we focus very much on EM techniques because they are able to measure the electrical resistivity or conductivity of reservoir rocks. And as showed earlier this morning by Benoit, these are very important parameters to monitor simply because it's pretty much sensitive to the presence of fluids, its chemistry, its temperature, its volume, and so on. So it's a key parameter to actually map, but also to try to monitor. The field of EM monitoring is becoming more popular, but I still would like to stress that this is still ongoing research. There are very few studies around the world doing this type of measurements. I just show here a graph to summarize the motivation behind measuring resistivity during thermal stimulation. It's simply because when you increase by roughly 100 degrees the temperature of a rock, it's doubling its conductivity, electrical conductivity. So it's a parameter that is actually very sensitive to temperature. So what we did during this DPGS project is actually to test two types of techniques. The first one was actually a passive technique, which is called magnetotellurics. The drawback of this technique is that it's very much sensitive to the variation of the natural Earth magnetic field. So you're never sure whether you have a good or bad signal. And the second technique we tested is actually an active EM technique, which uses an artificial transmitter. So this one is actually pretty much new. It's not been much applied in geothermal. So we've tested it in over the Reykjanes field with two types of surveys. One with a joint CSEM and MT survey, which we call time lapse. So it's basically making two snapshots at the reservoir at different times. And the second type of survey was actually a continuous MT survey when you continuously record the Earth magnetic field and try to infer subsurface changes. This is the layout that we've deployed around the Reykjanes geothermal field. I must acknowledge ISOR here because we also use their MT stations acquired before this project. We had two time-lapse CSM surveys, which are in 3D, covering the whole area, and a few MT stations continuously monitoring the Earth magnetic field. Here I'm just showing you a summary of the different results of the surveys. This one is just to show you at the top graph a spectrum of the currents that we inject with CSEM. And at the bottom, it's showing what we record. And we basically record peaks of high energy signals well above the background noise or background Earth magnetic field, which warrants very high signal to noise ratio measurements independently on the presence of industrial noise in the area. I'm saying this because we also observed that during these surveys, passive measurements, natural magnetic fields are challenging, especially MT. Actually, during our baseline survey, we could not extract much signal simply because the rigs were drilling and a lot of noise was generated. So time-lapse MT is still a very challenging task, and in our case, we did not manage to make it work. The results that we obtain are twofold. First, on the imaging side, do we manage to get a good understanding and the description of the subsurface resistivity? We think we do by combining both CSEM and MT measurements. It's showing you here a cross-section versus depth and distance across the Reykjanes field and cutting the RN15 IDTP2 well. The color shows you the resistivity in log scale, and the bar in the middle is actually the logged resistivities. You see a pretty good agreement between the observed resistivities in the well and what we recover away from the well from the surface measurements. So this gives us confidence that we have actually good data to play with. So we went ahead and repeated the survey and actually tried to develop a protocol that gives us high repeatability for this type of measurement. And here I show you an example of measurement. The red and blue curves on the left is the electric field spectrum during 2 years apart, basically. And the right is actually the ratio. And we observed that our measurements are repeatable between 1 and 10%, which is fairly high. And we also learned that actually the signal to noise controls this repeatability. So we were pretty happy to see that we have repeatable measurement. Unfortunately, we did not manage to pick CSEM signal up between the two years. And we think it's due to the fact that the sensitivity of EM techniques is actually very dependent on the volume over which the resistivity change occurs. And because this graph shows you here a model response of the sensitivity of the system versus the volume of the area, that is where resistivity had changed. And what you see with these curves increasing from left to right is that the higher the volume, the larger the volume, the higher the response. And actually the volume over which the change occurs needs to be relatively large. I would say several cubic kilometers to be able to pick something up. And this was not the case between the thermal simulation of ADPP2. So this is our explanation for not picking up something. It's not because the technology does not work, it's simply because the sensitivity is probably low. On the continuous MT measurements, we picked some interesting signals up in between 2 seismic events, actually, during the drilling of the deepening of RN15 well. I show you here some MT transfer functions as a function of day with each color. And over a frequency band of 0.1 to 1 Hertz, we observed apparent resistivity changes that are above the noise level, but that we don't know yet how to interpret, whether they are related to fluid losses within the well during the drilling, or whether they are related to mechanical processes occurring within the reservoir, well, before or after this actually induced seismic events. So, be that as it may, these are interesting observations, interesting resistivity changes at the reservoir depths, but the physical model to explain it was beyond our study, but still we need to think about it. So to conclude this presentation, I think we can say first that the Reykjanes geothermal field is not an easy field for performing EM monitoring, simply because there are a lot of noise, and that really killed our time-lapse MT surveys. But by using CSEM transmitter, we actually managed to get good data sets and have a technology that is able to monitor resistivity changes at depths. Similarly, continuous MT can actually monitor resistivity changes at depths, but this is very dependent on the data quality and strength of the Earth magnetic field and presence of noise. So this is quite a challenging technique still. We think we have a tool that works, but as I said, that has limited resolution at present, and as shown by this example. And we are working on different solutions to increase this resolution to be able to, in this type of cases, be able to monitor changes. And we have 2 options, either to increase the power of the transmitter, we are currently working on this, or to deploy borehole magnetometers downhole, close to the reservoir, to increase sensitivity. And similarly, we are developing a tool to do that. So that's all I want to summarize. There are a lot more to say. We have actually published 1 paper on this, where you can find more details. And a second one has been submitted and hopefully will be accepted and can be communicated later on. Thank you.
In the next talk, I'm going to speak about the developments that we have done in the development of the wellbore simulator and the applications to RN15 at the DEEPEGS project. Sorry, yeah. The general aspects of a wellbore simulator is the modeling of the characteristics of the borehole fluids as a function of depth, a function of temperature, pressure, and also of salinity during production and injection conditions that can dramatically change. We also need to be accounted for parameters like friction, the heat transfer, chemical reactions that can take place in the borehole. And we also, and this is a special aspect of the Reykjanes well, RN15, is we have to quantify the transient state of the borehole profile. The goal of the wellbore simulators is, of course, before drilling, the design of the well, and after drilling, the determination of key factors like the static formation, pressure, or total and overpressure at the bottom hole conditions out of wellhead data. And therewith, we will be able to decrease, and we should contribute to a decrease in the log operations and also to improve the cost, the economics of the well, the drilling. In the framework of the DEEPEGS project, we have done some further development of the capacities of our wellbore simulator. And this was especially applied to the Reykjanes borehole RN15. And you will see that I will give you some examples on the complex conditions that we have encountered at RN15, which are due to the drilling effect, due to the logging conditions. The intention was to derive parameters of the underground in this highly transient state. In addition to RN15, we also contributed to the borehole FDH GT2 in Vendenheim in France, a talk that you will see later on this afternoon. Looking into the situations, specific situations on RN15, is that there was a continuous injection during logging. So all the logs are heavily perturbed by the injection conditions occurring during the drilling and during the logging itself. And moreover, it is not only a uniform injection, it was a changing injection in a coaxial flow condition. So there was this idea that, first of all, we had to evaluate and look for a wellbore simulator that was able to have a transient, to develop this transient state, and also to run in borehole conditions in a coaxial flow. On the right, you see the validation that we have done to their different analytic solutions. And I just show you here the solutions of Bobok and Zaka, where you see that our borehole simulator is showing the symbols, and the straight lines, continuous lines, are on the analytic solutions. So this is a very simplified situation where we could reproduce nicely the Bobok and Zaka model. On the next slide, I introduce you. Sigurður, you don't. On the next slide, I show you the transient aspects. We already mentioned that the flow was, all the conditions have been evaluated under injection conditions, and these injection conditions were not continuous, but were disruptive in a way, and were completely changing. And on the topmost left part, you see, for example, the flow rate changing during a log itself. And of course, the change of flow rate is dramatically changing the temperature field in this log. Another aspect is also what you see on the green, the blue screen here, is that you see the time as function of depth of the logging speed, but there's changing logging speeds, and each of the logging speed is a transient state, and that, for example, can create a bubble here in the temperature log that you see here. So we are also able to reproduce the changes, the temporal changes during logging in the response of the log parameters. GIA has done a poster on this. So one of the documents that you can see is a poster and the publication of GIA that is done on this developments. Another case is, of course, the continuous deeping of the well. also the continuous deepening and also the continuous changing of temperature in the well had to be reflected by the borehole simulator. And therefore I show you just this is a very small change that you can see here onto deepening, but there are higher impacts if you consider different deepening periods. So one of the interpretations that we have done was on the log from January 3rd that already was shown by Seta this morning. And we have applied a joint inversion on this temperatural profile. And we came up to different scenarios that are rather close to the results of Seta also. But you see that the static formation temperature in 2.5 kilometers is something that we evaluated to be close to 400 degrees C. And what we see here in 3,400 meters is a change of the temperature. And the change of the temperature is interpreted, of course, in agreement also to what Seta has done and has shown, is interpreted in a flow. It's a major flow loss zone that we encounter here. And so behind the flow loss zone, we only had 90% of the fluids that can be encountered that are here. And so there's a dramatic change on flow rate that is reflected in the temperature log itself. And we come up at 4,200 meters here on temperatures of roughly 500 degrees C. And in the lowest part, we will our log interpretation by this innovative borehole simulator comes to 520 degrees C. The wearable simulator, as it stands right now, is able, I showed you this, to reflect the pipe physics. Pipe hydraulics, one-phase and two-phase system, is able to get these highly transient dynamic solutions that I have shown, that we have had in the RN15. But furthermore, it is a fully coupled system as well. This is on temperature, on enthalpy, on pressure, on viscosity, on the equation of state. Everything is integrated here, and it's also a multi-component system in which we can include different different mineralizations. The solver is massively parallel constructed, and we are just currently working on its integration into the reservoir simulator in Tiger, our reservoir simulator, so that we can have both the reservoir simulator and the borehole simulator and look on what happens if we make changes to the system. In conclusion, it was a highly challenging aspect, and it was a fantastic aspect to work on RN15. So we had our application to RN15 was not easy to be achieved, but it was fantastic to work on this. More innovative capabilities are continuously added to our borehole simulators with a focus on aqueous chemistry and reactive multi-component transport. We will also enable the scaling formation processes in the borehole, as well as the definition of corrosion potentials along the borehole profile. There are some publications that have came out of this. They have shown here in the references. Another publications are going to follow in short while. Thank you very much for your attention.
Yes, good evening, everybody, and good morning to those in US and other places in the world where we don't have the evening. But I'm going to talk to you about flexible couplings for geothermal wells. Actually, it is a continuing effort from a GeoWell project, which you learned about earlier this afternoon. In the GeoWell project, actually, we did two couplings for 958 casings. And in this DBGS, we take the 958 up to prototypes for 1338 and then to full production for a geothermal well. We have obtained 2 patents before a DEEPEGS project started on this technology, and we have published a number of papers for it. So you can find a lot in the web. But the purpose of the flexible couplings is to avoid plastic straining of the casing, and by allowing the axial displacement of the casing, the production casing, into the couplings. This is due to the fact that preliminary studies in ISOR have shown that most of the reported incidents in wells we find is due to buckling, to actually plugging, some kind of choking, could be from bulges. We haven't got the camera down to verify everything, and then to casing burst rupture, tensile rupture, and so on. So actually that's the need for some kind of technology to cope with the plasticity of the casings due to the high axial load of the thermal expansion is needed. So we have designed this and we have tested it, and actually before we tested it in real sizes and full size prototypes. We did a lot of calculations about the strength of the material, the design of the coupling. We applied to all the standards who are needed to actually or applied in this industry. We designed it with buttress threads. It's made of L80 for the K55 and L80 casings. It's no problem to go into titanium, nickel alloys, or higher strength steels if needed. And this coupling allow clearance according to standards for cementing, just like any other couplings today. So there is no need for training or operational issues on the drill rig, and it should be the same operation for them as usual. But let's look a little bit to what the coupling does. In the left, you have the conventional couplings. On the right, you have the premium connectors. When you heat up, actually the well, the casings try to elongate because of the thermal expansion of the material. In the conventional couplings, you take this load because you have locked the casing into the connector. You take this load up in the threads of the casing connectors. In the premium casings, you take this up as a pressure between either as material in the coupling or between the casing segments who are, so to say, kissing each other. So this means that during the heating, the pressure is taken up elsewhere in the premium connectors than in the casing connectors, the conventional ones where it is on the threads. But when you have the need for cooling down the well, you have plastically deformed all of the casings. So now you try to pull them out of the connectors. This means that the same situation in all cases, although you have the premium connectors situation as you have in the conventional one, that the load is taken up by the threads. So no change in that, and that's why the premium connectors have been designed with a very good load-bearing threads, and even that is not enough, as we have seen in, for example, IDTP1. But let's go to the design of the flexible couplings. What I said earlier is that we want to do it by avoiding plasticity in the casing. That means that you have to allow the casing to slide into the coupling, and by that you take away the loads or the strain or the stresses, to say, because you are in the linear part of the stress strain curve. You take away the plasticity and you allow the coupling to move, or the casing to move in the linear area. So actually you never go above yielding, and that means that you don't have the plasticity, which will generate high tension when you cool down the well again. So in principle, the coupling is very simple. When we heat up the well, the coupling slide with the casing and close. This means that you take away some displacement and you can design this LT according to the temperature you will have in the well. Every coupling is with this capability, so it is 12 meters between the couplings. So the total length of the production casing is with these new couplings. And if the needs comes for closing down for maintenance or for any other reason, you slide again up. So you have the same situation and you can repeat this without the risk of tearing away the threads or cutting off the casing. We have tested this in 2 independent laboratories in Norway. First, in the Geothermal project, we tested the 958 couplings in both bendings and in straight position. And in the DEEPEGS project, we have been testing 33/8, a wider diameter casings connectors in sliding in a straight position. So if everything goes well, you can see now when the load comes, the casing slides into the coupling. And when we actually have to cool down again, we have the casing to slide back. And we have tested in 8 prototypes this sliding capacity, and it's shown to be repeatable and without any locking or sticking or anything that can prohibit the casing to move. And as I said, these are 8 tests we have been doing, and we have the ultimate tensile loadings, because that's very important when you are lowering down the casing, that you have the capacity and loading capacity of the coupling to cope with the length of the casing, the weight of the casing. So we have defined all these parameters. We have tested in 2.5 bending when we are not with a straight well, with deviated well. That's more than we have seen in the geothermal industry. We have doubled that up to 5 degrees bending, and still we have the same sliding force in all cases. So that means that we have not observed any sticking or sliding problems within the casing. So as it is now from the end, at the end of the DEEPEGS project, we have manufactured 87 couplings. We have tested 2 of them. We have 85 now ready for running in whole, and that will cope for approximately 1,050 meters length. And you can see on the right how the couplings looks now when they are painted in the according to standard with actually the needed information on them. So this has been quite an experience for us, and we have been working a lot with the finest equipment we can find to measure everything we do, and to actually look into all kinds of influence from parameters we have been monitoring. And we think that now we have the product ready for full-scale demonstration. And that demonstration is planned. We don't know really, but it's planned to be very soon in a well, probably in the Reykjanes, no, in Nesjavellir area, or later on in the Reykjanes area. But we are not at the moment capable of telling more about that. So thank you for the attention.
Hello. Good afternoon, everybody. My name is Dennis Wollmer. I'm working for a manufacturer called Reykjanes Vertical. We are manufacturing rigs as well downhole technologies in regard of new drilling, innovative drives. And for the DEEPEGS project, it was our aim to manufacture and develop in order to demonstrate a new drilling technology for high pressure, high temperature requirements. You see here on the left our demonstrator, which consists of, on the left, the electromagnetic drive, which is a percussive drive at the end. And on the right side, you see the controls as well, the generator set, which is connected at the end to a turbine. And during the presentation, I will go through the main achievements in this project. The challenges and next steps will be highlighted. As well, I will do a short dissemination and outlook for the future of this tool. So the actual achievements, what was the main drive here? This project was as well in collaboration with the Technical University of Freiburg. They gave us certain input for percussive drives. We have selected a percussive drive for hard abrasive rocks because they have the highest rate of penetration potential. The main drawback of those drives was at the end the bottom hole time. So they had a very high erosion due to high velocity rates of the flow inside of the channels to amplify the piston up and down. And in this project, we decoupled the mud flow from the main drive and have now put a generator set connected to a turbine in between to get the necessary electrical output to drive a reluctant electromagnetic drive at the end. And we received from the tuber from the Technical University of Freiburg the main characteristics which are required to destruct the rocks with percussive drives, which are around 200 to 300 joule. We require at least an impact velocity of 2.5 meters per second. And we are looking at frequencies of 10 to 20 hertz. As well, in regard of the power supply, we concluded a minimum required energy input, which was around 50 kilowatt. And we looked at certain turbines, for example, supplied by Schlumberger to drive the generator sets. We concluded based on the tests that we have received sufficient impact velocity. However, the impact energy was not sufficient, unfortunately, in the test so far. However, this can be later on as well improved in the next step. As well, we had some higher friction forces. As well, we had eddy current losses, which resulted, unfortunately, to higher ampere requirements, which at the end resulted to the lower impact energy. The controls were developed for high pressure and high temperature as well, and were actually developed for 70 amperes. So that means for the deployment in the bottom, we would have to adjust those controls to the higher ampere requirement, or we are going to remanufacture the piston to reduce the eddy current to have higher impact energies available. This is how the tool is broken down based on our 3D design. So as mentioned, on the top you see the reluctant drive driven by coils. And we see as well in the midsection the generator set on the right, which is yellow, and on the left the control section, which is connected to the main drive in the front. And as well, we do look at the turbine, which will be as well coupled to this equipment at the end. Just waiting for the next slide. Right. So as mentioned, we saw quite high losses in our test results. We unfortunately have a efficiency of 2.5%. Based on our calculations, we would require 25% efficiency, which is easily can be easily achieved in the modification, as mentioned, of the piston as well of the controls. The higher current requirements at the end is the result as well of the eddy current issues. The full piston stroke is currently 24 millimeters. Should be also a little bit adjusted and improved to up to 30 millimeters as well. This can be as well rechecked and adjusted in a later stage of this tool. When we look at the dissemination at the end of the tool which we have built and tested so far, we look at the status quo, which would result in a very low rate of penetration of around 0.15 meters per hour. However, with small adjustments, which are requiring some further resources as well, some further time, we would be able to achieve the 25% of efficiency, which give us a rate of penetration, an average rate of penetration of 1.5 meters per hour at 30 hertz. The whole tool is developed to drill 12.25 boreholes at flow rates up to 3,000 liters per minute to drill at the end for the production casing of a 958. The outlook overall is the modified mud hammer in the future, based on this, would be competitive to conventional drilling methods in regard of higher or longer bottom hole times. We are able to achieve the double lifetime of this tool compared to conventional drives, which would us allow to complete production casings 2 days ahead of normal drives, mainly. Yeah. So the tool, due to several delays, unfortunately had been not able to deploy it in a real well so far. However, we have deployed the tool in different high pressure and high temperature testing facilities, as well as laboratory tests to do functional testings, as well in test. And the tool has been currently put in storage. You see here on the left, while we put the tool in the box and waiting currently for a project, near future project for this tool. Thank you.
We start the presentations of the Vandenheim Demonstrator with a brief history of the site, a description of the drilling with, in particular, the multi-domain aspects, and a description of the test carried out. So I'll just click. I click, but okay, that's okay. The Vandenheim drilling site is located in eastern France, in Alsace, near the city of Strasbourg. The first studies began almost 10 years ago in 2011. The exploration license was granted in 2013 after 2 years of procedures. In 2015, the acquisition of seismic data made it possible to specify our target and request an authorization for drilling. This was obtained in March 2016. The Microseismicity Observation Network began its observations in July 2016. And after a necessary observation period, the first drilling could start in June 2017. The first well was tested in March 2018. The second drilling was completed in 2019, as well as the drilling and the test of the second leg on the first well. Currently, tests are underway on the second well. You can see on the photo the current rig used for well 2 and the second leg of well 1. You can see all the equipments and the technical containers, as well as the offices building on the right. On the left, you can see the pools used in particular for the test. The site is on the location of the former refinery, and this site is undergoing rehabilitation to become a new place for business development in the Strasbourg area. The Forge geothermal power plant will be fully integrated into this industrial park and will allow the geothermal heat to benefit to industrial users. The photo offers a preview of what the future park could be. And Forge also plans to develop a fish farming facility in this area connected to the power plant. Here are pictures of the rig used for DEEPEGS. It's an automated and silent rig. It has a lifting capacity of 450 tons. On the photo on the left, you can see the robotic arm to load the drilling pipes. Our objective was to develop the concept of multi-drain in order to improve the productivity. The well 1 was drilled, cleaned, and acidified and tested in early 2018. In order to set up a multi-drain, we conduct a reflection on the different possibilities and technologies usable in this difficult geological context. Difficult because of the depth and the temperature. We finally chose to create a sidetrack and to drill a second leg parallel to the first one until reaching the acidified zone in order to benefit from it and to enhance the performance. The trajectory is drawn here in red. It follows the trajectory of the first leg by wrapping itself around it and remaining at a distance between 7 and 25 meters in the lower zone of the well. The image on the right is a zoom on these two trajectories. In order to meet this challenge, we were unable to use real-time directional drilling tools with downhole motors. Indeed, they remain effective up to 150 degrees, but they fell beyond that. However, we have temperatures of around 200 degrees at the reservoir level. We therefore manage the trajectory using different bottom hole assemblies in order to adjust the drilling angle to stay at a distance between 7 and 25 meters, taking into account the degree of uncertainty of the real trajectories. Here are the different types of assemblies used. Each one has more or less important number of bed stabilizers, which conditions the angle of the trajectory. The first one keeps the trajectory angle. The second one will decrease the angle of the trajectory. And the third one increases the angle of the trajectory. The sequence of assembly choice and the control of the wear make it possible to supervise the trajectory thanks to our experience on the first well. And the logging carried out at the end of the drilling confirm the good performance of this trajectory steering. Just some words about the status of the Vandanen Demonstrator. The two deep wells drill almost 5,000 meter drill. And we see in the next slides the different wellbore diagram. The second leg of the well 1 is successfully completed, and the tests are underway on well 2. This is the diagram for the well 1. It shows I can point out that it shows the exchange zone with the reservoir improves the drilling of the second leg that you can see on the bottom of this diagram. On the diagram of the second well, it's important to note the long length of the open hole parts, which represents 2,600 meters between the Permian and the basement. The macroseismic monitoring network has been modified and densified along the site in order to improve our interpretation and our forecast. We went from 5 stations at the beginning to 40 stations. The drilling site is indicated on the diagram on the map with a red flag, and the black line corresponds to the trajectory of the first well. The macroseismic interpretation made it possible to improve the precision of our knowledge of the structural context. You can see on this diagram the top Permian and the top basement, as well as the 2 large faults identified by the seismic imagery. These faults constitute our targets. The macroseismic interpretation with the location of the events made it possible to locate these 2 faults with precision. And to confirm the fault North 70, which was not visible in the south with seismic. Well, now let's have a look on the test. This is a picture during the test. And the test on the dual legs, what we can call multilateral, have been done on the first well. And the tests are ongoing on the well 2. And we plan to have tracing and dual tests during next month, in May 2020. The methodology used includes 10 phases. The phase 1 is the log of the static characteristic of the well. The phase 2 is degorgement of the well with production in airlift. It allows to make a first cleaning and to obtain the artesian pressure, the initial productivity index, and the geochemical signature of the fluid. The phase 3 is the cleaning of the well with circulations comprising acid. The phase 4 is the injection test, which calculates the initial injectivity index and cools the well before the chemical stimulation. The phase 5 is the chemical stimulation in order to dissolve mineral filling faults. The reactive is adjusted in function of the rock to dissolve certain minerals related to fault filling, like calcium carbonates, halides, smectites, chlorides, and barium sulfates. Normally, a mix of organic compounds and mixes of hydrochloric acid and hydrofluoric acid are used. The phase 6, it's the first phase of hydraulic stimulation within the limits provided by the administration. It's 100 bars. It will improve the hydraulic performance of exciting structures. The phase 7, it's a new log in order to identify the productive zones. Phase 8 is a production test. This we are going to develop the well and to estimate the potential of the well. The phase 9 is, in fact, a second phase of hydraulic stimulation. And finally, phase 10 is a thermal stimulation with injection of cool fluids. Thermal stimulation is driven by thermal contraction caused by significant temperature difference between cold injection fluid and hot reservoir rock formation, which can enhance near wellbore permeability. Here are some elements quantified during our various tests. On the graph, you can see the flow in blue. The pressure is in the casing is in green, and the pressure in the pipes are in red. The tests are carried out with progressive steps of ascent and descent in volume and pressure. And this is necessary to verify the reservoir response and limit the macroseismic events. During all tests, real-time monitoring of induced seismic events make it possible to alert and adjust test operations. The initial injectivity index let us calculate an injectivity index of 0.4 liters per second per bar. The chemical simulation was targeted on the 3 areas at different depths. The injectivity index gradually improved to 0.6 and then to 1.1 liter per second per bar. The hydraulic stimulation, which followed, made it possible to reach 1.8 liter per second per bar. The pressure and temperature log in the well identified 2 color zones. And the production test took place over 48 hours after a rise in pressure and temperature over 2 days. Artesian production reached 100 cubic meter per hour, and the productivity index was between 1 and 2 liters per second per bar. Thanks to the second leg, we can see an improvement of the injectivity index from 1.2 to 1.8 liters per second per bar. Oh. Now we are very close from our industrial objective, and actually the power plant is under construction, as you can see on the photo, and we expect the first electric power production in September 2020. Thank you for your attention.
Hello, everyone. The aim of this presentation is to share with all of you our current understanding and our current pictures of the Vandenheim reservoir through a conceptual model of this reservoir. This conceptual model is based on all the data we can have, geological data, geomechanical, geochemistry from fluid and all data, fluid flow and all data we can have. It will be the base for all the following analysis and numerical modeling we are going to present. So the idea is to have a unique model to integrate and unifying all the knowledge we have on the Vandenheim site. So, yeah. First about the geological context. Vandenheim is located in the Upper Rhine Graben, which is a part of the European Cenozoic rift system. You can see here on this picture. And Vandenheim is located here, very close to the well-known Soultz-Soufforêt pilot site. It was, I think, the first EGS pilot site in the world. So you can see that this European Cenozoic rift system is actually an aborted rift system, and is very well known because it's the thermal anomaly associated with the rift system. And the thermal anomaly in this rift system is mainly due to the uplift, the thick sedimentary blankets. Actually, above Vandenheim reservoir, we have 4 kilometers thick of sedimentary layers, and mainly because of the granitic nature of the basement. So Vandenheim is located inside the right graben, and it targets a fault, a north-south, mainly north-south fault, dipping to the west, which is a normal fault for now, but probably pre-existing during the Hercynian orogeny. So the target was very deep, around 4.5 kilometer depth, because the target is to have more than 200 degrees. So we will be in the basement. So the Upper Rhine Graben is a well-known area for geothermal extraction, and it was the first site for the Soultz-Soufforêt pilot plant, which is something that's 40 kilometers far from the Vandenheim site. And from more than 30 years of studies and analysis on this area, we have currently developed an idea of the behavior and of the geothermal system. For now, and for our understanding, we have a feeding zone in the east part of the Rhine-Graben. The next or the later presentation of Bernard Saint-Jean will explain why. It's mainly based on the geochemical data. And we have an outflow area in the west part of the Rhine-Graben. Fluid circulates mainly through the fault and through the discontinuity in the basement. And Vandenheim is located in the global area where we have outflow. And as we have similar fluid composition for Vandenheim, Sulz, but also Rittershofen and so on, we think that it's the same geothermal system. If we have a closer look to the Vandenheim area, the target is a fault, expected to be the reservoir. The fault is very big fault, probably inherited from the Hercynian orogeny, maybe with a movement of strike slip at this time, and then move again during the Oligocene rifting as a normal movement. This fault is very important. We have more than 600 meters of offsets on each part of this fault, and several secondary antithetic and conjugated faults, mainly in the sedimentary part, are observed. You have here a sketch of our current understanding of the formation of this fault. So it's a very big fault, as said, and as we have a big offset, more than 600 meters, we expect that we have a thick, very thick structure between 150 meters and 300 meters, composed with several secondary structures with a fault core and damage zone. So the first one of Vandenheim, GT1, crosses the fault in the basement with an angle of around 40 degrees, as you can see here. And for now, the main question is, what is the inner structure of the targeted fault? It will be control the flow in our reservoir. So the results I'm going to present are based on the knowledge we had during the DPGS project. That means that we are based mainly on the data from the first well, GT1 of Vandenheim. So in GT1, we have no logs in the basement because mainly of wellbore stability issues. So main knowledge is based on the data from the drilling, losses, and we can see you have here a map of the well trajectory, and we have several areas with big losses. Main losses are located in the upper part here. And we have also information from the ROP break. That means that we have weaker structures in our reservoir. So in the red circle, we have many ROP break during the drilling. And also the last kind of data, it's from the cuttings, and we have the petrology. And then we have seen that we have first an altered rock mass, and then an area with several cuttings with erythral quartz. That means that we have a sealing of the discontinuities in that. And at the end, we have a cataclastic rock. So thanks to this data, thanks also to the knowledge we have on the fault structure in the Upper Rhine-Graben basement, mainly based on the data of Sulz-Forêt and analog sites close to Strasbourg, we have defined a conceptual model of the fault, and we have interpreted all this data like that. So we have a big fault with first a damage zone located of several fractures, more or less open, filled with clays and with carbonates, as seen by the cuttings. And then we have the fault core. The fault core can be split in two areas. First, we have a core with very low permeability because it's silt. We have silt discontinuities, many gouge, several clays, and so on. And then we have a fault core that is mainly cataclysm areas. So we have many discontinuities, and within we can have flow, as shown by the losses observed during the drilling. So the main question for geothermal exploitation and the reservoir model is how is the flow in the fault reservoir? So we have to make many assumptions and tested different kind of configuration in numerical modeling to have all the possibility. So our main assumption about the flow is that we have probably a feeding zone upward through the fault. And then we have output of the flow, maybe in the sedimentary part. We have several permeable sedimentary layers in the sedimentary part of the Rhine cavern. And probably also we can have outflow in the damage conjugated zone. And then inside the reservoir, inside the fault, we have on the damage zone flow through the discontinuities mainly. And then we have probably a silt zone, quasi-impermeable, looking at the flow in the discontinuity in the upper part. And then again, a transmissive area, because this part of the fault core is very heavily fractured. And so it can be maybe something that equivalent to a porous media. So this is our current understanding and our current pictures of the reservoir in Vandenheim. So conclusion, for now, we have very few data from the first well. There's no more much data in the GT2, the second well. So we will be able to build a first conceptual model of the reservoir with the following characteristic. We have inner structures of the fault that impact the fluid flow. We have different zones, permeable and not permeable. But we have a lot of unknown that remains. We don't know exactly the detailed structure of the fault zone. For example, what is the secondary fracture orientations? Where are the feeding zone? Where the flow go out? And what is the main fluid pathway in the fault? Nonetheless, the work is still ongoing, and we have now the second well drilled in 2019 and 2020. And it will give new data for the improvement of the fault model and the lateral evolution of the reservoir in particular, because we have more than 1 kilometer between the two wells. And we would like to stress also on the analysis on the induced seismicity to have a better understanding of the fault structure and organization of the reservoir. Also, there are several tests that are planned for this year: well test, interference test, tracer test, and all that test will give us data for improve the knowledge of the reservoir. So beyond DPGS project, we hope to go toward a model of the full reservoir, including the both well of Vandenheim Demonstrator. So, thank you all.
Hello, everybody.
This presentation is related to the stimulation performed at the Vandenheim Demonstrator and focus on numerical simulation to study the impact and the efficiency of stimulation methods. So one of the main technological challenges is to optimize well architecture and stimulation methods to increase flow rate in deep hot reservoirs that initially offer little production. And these technologies are scheduled based on expert advice, but this preparation lacks the prior study of the base planning. For example, a scenario which gives the most beneficial increase in injectivity. An ideal prior study should incorporate a reservoir model that would serve as a command base for several predictive numerical tools. A workflow stimulation method could then be run for investigating the best scenario. That's why this numerical work carried out for the Vandenheim Demonstrator was focused on building an approach and specific procedures in order to obtain a qualitative characterization of the respective and successive impacts of the different stimulation technologies. This approach is based on the use of a single hydrothermal numerical model, allowing to simulate an injection test in order to assess the injectivity index, while integrating the results and the constraints provided by other specific numerical models, which can simulate thermal stimulation or hydraulic stimulation. So the first step of this approach was to build the 3D geometry. And due to scarce data at targeted depths, the geometry is based on the extrapolation of fault network from well evidences, from the global tectonic history, and from the use of a generic concept of fracturing. The domain is a block rock of 500 meters cubed and centered on the open hole of the well. The domain is composed of 4 subdomains: the surrounding matrix, which is impermeable; the damage zone, which is impermeable, where the matrix is impermeable and composed of fractures, which are more or less permeable; the first fault core, which is where the matrix is impermeable and composed of fractures seeded; and a second fault core, which is permeable. This numerical model is based on a hybrid approach, which enables to integrate the fracture network into the 3D matrix. And this numerical model is built using the Compass platform. And then to carry out model computations, boundary conditions along the faces of the model are prescribed. And using the initial injectivity index and an injection test, the hydraulic properties of the model have been assessed. Then we obtain the initial reference model to study the impact of different technologies. And then simulations are performed in order to assess the injectivity gain through different technologies, the well architecture, the hydraulic stimulation, and the thermal stimulation impact. So for this study, the results issued from the initial reference model and the injection test are used as a basis to assess the impact of each technology. The first technology tested is the well architecture. And to assess the impact of the well architecture, a secondary branch issue from from the primary well is implemented into the hydrothermal model. Then the injection test is performed, and we can compare the results with the results of the initial reference model. And we can observe for the well architecture that we have a decrease of the maximum pressure differential and a decrease of the maximum temperature differential. So to summarize, the well architecture multiplied the injectivity by a factor of 1.4. The second technology tested is the hydraulic stimulation. So as mentioned previously, we use the initial reference model and the results issued from the injection test as a basis. The hydraulic stimulation is performed through the use of a hydromechanical model using the 3-deck software. And the hydromechanical model simulates the effect of fault reactivation and modifies the initial permeability distribution among the fault network. So we obtain a new map of permeability, and this new map of permeability is implemented into the hydrothermal model. Then the injection test is performed, and we can compare the results with the initial reference model. So for the hydraulic stimulation, we can observe a decrease of the maximum pressure differential and a decrease of the maximum temperature differential. To summarize, the hydraulic stimulation multiplied the injectivity by a factor of 1.5. The third technology tested is the thermal stimulation. So here we propose the investigation of the impact of the thermal stimulation on the injectivity of the reservoir, and to assess the impact of the fracturing induced by thermal stimulation. A two-step approach is employed. The first step consists in the investigation of the potential fracturing at the grain scale using the code PFC2D and using a discrete element method through a 2D cross section around the well and around the fracture, as you can see on this figure. And these results of the thermomechanical model provide a range of permeability evolution as a function of the thermal gradient. So using this basic criteria, we can modify the properties of the reservoir in accordance with the temperature differential, which results from a cold fluid injection into the reservoir. Then the second step of this methodology is to simulate the injection of a cold fluid at the reservoir scale and use the thermal field, the construct of temperature to identify the thermal crack zones. And then we can modify the permeability according to the thermal field. And then the injection test is performed. And we can observe for the thermal stimulation a decrease of the maximum pressure differential and an increase of the maximum pressure differential. To summarize, for this specific case, the thermal stimulation multiplies the injectivity by a factor of 1.2. Then we propose to investigate a few scenarios of stimulation. The first scenario corresponds to the combined impact of the well architecture followed by the thermal stimulation. And in that case, the injectivity is multiplied by a factor of 1.5. The second scenario corresponds to the combined impact of hydraulic stimulation and thermal stimulation and results in injectivity multiplied by a factor of 2.1. And the third scenario corresponds to the combined impact of hydraulic stimulation and well architecture. And the injectivity is multiplied by a factor of 3.2. So a brief summary of the main results. For this specific case, it appeared that the different methods investigated, so the well architecture, hydraulic stimulation, and thermal stimulation, lead to the same order of magnitude in terms of injectivity improvement, even if these specific results show a slight difference between these methods in favor of the hydraulic stimulation and the well architecture. The successive effect of the hydraulic stimulation and the well architecture appears highly beneficial to the reservoir injectivity. And then to conclude, so first, the main aim is achieved. We provide an approach to obtain qualitative characterization of the respective and successive impacts of the different stimulation technologies. Indeed, we can observe that the impact of each technology is clearly different. So using the distribution of pressure and the distribution of temperature. And we can observe that the zones impacted and their relative efficiency is clearly different for each method. Moreover, the scenarios demonstrate that the operations order matters. The zones impacted and the efficiency of each technology is conditioned by any upstream technology employed. And so, even if further studies are required, the import of constraints provided by other but adapted numerical codes into this unique hydrothermal model offers a way to test different scenarios of stimulation. So, thank you for your attention.
Okay, good afternoon, everybody. Actually, I'm going now to discuss on the seismicity which was induced in the Vandenheim EGS site during the different stimulations we are going to look at. This work was performed both by KIT and by Fonroche. So from Fonroche, Marine Jolivet was working on this, and for the KIT, I was mainly working on this with, of course, some colleagues from the KIT. Sorry, I was a bit fast. So the seismic monitoring, as was said earlier by Lionel Boucher, was composed of different parts. So there was one part which was actually made from the permanent network deployed by Fonroche. And this was made about by 5 stations, which are here, these squares. So 5 locations here, which are basically on the north, south, and east side of the wells. And these stations, interestingly, had different combinations of sensors. So sometimes there was a single surface sensor, but we could also have multi-sensors in shallow wells, and even 2 levels in the wells which were a bit deeper. This network actually was deployed 6 months in advance of any operation on the site. So this is something which is mandatory according to the French regulations. A bit further away, still from this permanent network, there were also 3 stations still deployed by Fonroche and maintained by Fonroche, real time as the other ones, which were viable for the analysis. So in the frame of the DPGS project, the KIT deployed temporarily 4 stations, which are these ones which are shown here with the diamond. And basically we put some stations in the south and in the west of the 2 wells. So this was a bit to increase the coverage. And then you can see that we have a total of 9 stations monitoring in the radius of 5 kilometers around both wells. So this is what we can see here. The temporary network from the KIT started end of December 2018 and actually finished early this month. So the data we are going to focus on and the induced seismicity were recording during 3 main stimulation operations. So you may remember some slides from Lionel Boucher once again, but basically we are concentrating on the hydraulic stimulation of the well VDH GT2, and this is starting end of April until about mid-May. And then we were focusing on the thermal stimulation of this similar well. Okay, so after a gap, thermal stimulation was carried out, and this operation took quite a while. And then we are going again to focus on a hydraulic stimulation, which was the hydraulic stimulation of VDH GT1. So overall, we are covering the year 2019, and we are covering from end of April to mid-November, a bit before mid-November. So how we did do the processing? There was, of course, real-time monitoring of the data and remote control of the station, especially from the permanent network, which was maintained by Forge. So they were carrying out the detection of the earthquakes. So they were using filtering between 5 and 45 Hertz with a very standard ST-LTA detection. And this was done on the 3 components to be able to detect both the P and the S waves. You can see actually on the right-hand side an example of an earthquake which was recorded, where we can see, for example, if we look at the bottom here, the 3 components here, we can clearly see a P wave arrival and S wave arrival a bit later with lower frequency content. And so, of course, that's one of the tasks, is to pick these earthquakes to be able to locate them. So the picking was done, of course, manually, automatically with the detection process, but this was checked manually to be sure that the pickings were correct. And then this was later located. For the location, we used absolute locations with the non-inlock software. And once the earthquake was located, then we were able to compute a magnitude for this earthquake based on the P wave energy or amplitude on the vertical component. What we also did is, and this is a process which is actually ongoing, is that we are improving the pickings. So there is pickings of the P wave and S wave arrivals with template matching and cross-correlation methods. And the advantage of this is to increase the consistency in the picking between the earthquakes, and this is actually going to decrease the uncertainties in the locations. So we can actually apply a new relative location techniques, either IPODD or master-slave techniques, to improve relative locations between the earthquakes. So I'm not going to present results about this because this is ongoing results and only partial results have been obtained so far. So if we look at the detection, we are going to review the 3 periods we monitored, as I said. And actually, this is the first stimulation. So we were looking at, which is the hydraulic stimulation of the well GT2. So you see different things on this plot. The points are corresponding to the occurrence. So the occurrence of the seismic events. So these events, the horizontal axis is the time. And so you see when these earthquakes are occurring. And basically, the y-axis for these events corresponds to the magnitude, which you can see on the right-hand side of this graph. Then you have other curves, of course. If you look at the blue curves, if you look at the yellow curves, or if you look at the red curves, this is going to show you the flow rate of injection or acidification or productions. So depending on the color. And in green, you see the variation of the pressure according to this. So what we can see in this graph, so during this hydraulic stimulation of the well number 2, 81 earthquakes were detected, and almost none of the earthquakes were occurring at the beginning of the stimulation. So when the flow rate was the lowest, also the pressure was the lowest, except here at the end of one of the last small injections, then we start to have some seismicity. And then what is clear, when we increase the flow rate, then we and the pressure is also increasing here, then we start to have some seismicity. And this is something we are going to see also for the main second stimulation in this case. What is interesting, and which is something we often see for EGS sites is that this seismicity is occurring during the stimulation itself, but of course it can last after shut-in. So when we stop injection, and this can last for quite a while, okay, although the magnitude usually is decreasing. The thermal stimulation, so here we are looking still at the second well, but the time scale is much, much longer, okay? You remember this period was quite long, and then we have been able to detect a bit more earthquakes, 208. And again, you see the distribution of these earthquakes in time and in magnitude. And you can see again several times, so you may have earthquakes during the stimulation or also after the stimulation. Especially this second stimulation was quite seismogenic with many earthquakes and during and after the stimulation. And this is the same for this third period. What is interesting that this third period generated a relatively strong earthquake of magnitude 2.2, which was not felt on site. And if we look at, again, the other injections, again, we can see that seismicity is induced, and this is also induced. And we have, for example, in this case, some earthquakes which are induced and which are really not correlated to any operation on the site. So that's really something we have to consider, and that's something we know for quite a while now for EGS sites, that we may have seismicity after the shut-in. Then if we are focusing on the stimulation of the first well, we recorded much more earthquakes, 475. And again, then you can see that we will have seismicity a bit for each of these different stimulations. When we have the production, and here this is this red curve here, actually we see that this seismicity tends to be much smaller in terms of number of earthquakes. Now we're going to focus a bit more on the location of this seismicity, and then I have to talk about the velocity models, which is something which is quite critical. So we have to define a velocity model to locate the earthquakes, and here it was made. We had two different approaches between the KIT and Font-Roche, and I'm going to show you the two location results. But both of us, or both of, we were actually working on the combination of the zero set VSP data and sonic log from the first well, so VDH GT1. At the KIT, what we did is that we used this 1D profile as a reference. So we are always working with a 1D velocity model, but actually we calibrated this model to minimize the uncertainty on the S-wave velocities down to 750 meters. Actually, the logs and the zero set, I mean, the sonic log is not providing any information about the S-waves. And this is the same for the VSP. In the shallower parts, so until 750 meters, so that we always have kind of uncertainty on this velocity. So to do that and to correct from these possible uncertainties, we actually did use the biggest earthquakes, I would say, which were locatable only using the P waves. And then we could, and which were also recorded by all session, and then we could use the time residuals as P and S wave time corrections. So that's how we are going to locate the earthquakes. And for the Font-Roche, they did a different approach. So they took into account the fault, the main fault they have, and they were drilling through for the second well. And they actually applied this 1D velocity model and shifted it a little bit along this fault to account for the offset of the fault. And they also did surface wave inversion to be able to have a good estimation of the S-wave velocities for the first 100 meters. So they were using this 3D model to locate the earthquakes. If we look at the location of the seismicity, so here we are looking at the first well and the hydraulic together with the thermal stimulations. We see on the left-hand side, so this is a map view of the epicenters, or map views, and both plots are similar. On the left-hand side, you see the results obtained with the KIT velocity model, and on the right-hand side, you see the results obtained using the Font-Roche velocity model. The color scale here on the left-hand side is showing you the relative time of occurrence of the seismicity. So most of the seismicity actually is occurring here at the beginning, and then it's moving to the end. So the end would correspond to the thermal stimulation, while the blue would correspond more to the hydraulic stimulation. What we see is that these earthquakes are located within 1 to 2 kilometers around the well, and they are pretty well centered around this well. If we look in depth, you have now projection. So projection along east on the west, on the left side, and projection along north on the right side. And you see that on the top you have the KIT locations, and at the bottom you have the Font-Roche locations. And here we see some kind of differences. For example, here we see from the KIT that it looks like we have 2 clear clusters of seismicity occurring during these operations, which is not so clear for the Font-Roche locations. And the other thing is that the KIT location usually are a bit more centered on the well. But in both cases, we see that this seismicity is occurring between 3.5 and 5 kilometers depth. Now, if we look at the hydraulic stimulation of the first well, again, we have a big cluster of earthquakes, which is again centered close to the well, both for the KIT model and for the Font-Roche model. But again, with the Font-Roche model, we have the seismicity which is a bit shifted to the west. And in depth, we have kind of similar results. So again, if we look at the projection to the east, we see that for the KIT, we are closer to the bottom of the hole for this seismicity. And for the Font-Roche, we are a bit offset from this bottom of the hole, again, due to the velocity model. The good thing, again, despite these uncertainties in the, I would say, XY locations, generally we have also the same depth range for the earthquakes, so between 4 kilometers and 6.5 kilometers depth. We also looked at the magnitude distribution, and what you see here is an histogram of the number of events for a given magnitude range. And we can see that we were recording earthquakes between minus 0.35 and 2.2, which was the maximum we've seen earlier. And this, with this, we could also compute, because we had enough earthquakes. So if we take all the earthquakes together, and if we compute the magnitude of completeness, which means the somehow the smallest magnitude we can record anywhere below the network, we reach a magnitude of 0.5 almost. And the B value is 1.17, which is a value which is a bit higher than the usual tectonic value observed, which is close to 1, and which is again consistent with induced seismicity and consistent with seismicity induced during stimulations. So to conclude, I would say that what we have observed is that in both cases, for both wells, most of the seismicity was remaining close to the wells which were stimulated, okay, in a radius of 1 to 2 kilometers. In the first case, so the second well, actually, we observed that 2 clusters seems to be activated during the stimulations, and the deepest cluster being close to the total depth of the well. For the first well, so GT1, and the hydraulic stimulation, we only observed one kind of big cluster, which was located below the total depth. What we also observed, which is really common, is that the seismicity occurred during and after stimulation. And we had a good, I would say, magnitude of completeness for this network, which is in an urban area. One earthquake was felt after the stimulation of the first well, and actually this led to suspend any injection and in operation on the site, injection operation. And there is an expertise which is ongoing on this earthquake. What I would say also as a conclusion is that we still have, because you've seen that we located using 2 velocity models, so we also have uncertainty in these velocity models. And this is really something which is very important and very common, a concern we have in monitoring. And this calls for calibration methods developments. So it would be important to try to focus on how we could really calibrate this velocity model, especially the S-wave velocity models, because this has a huge impact in the location, especially in depth of the earthquakes. So I think this is something we have really to think about and to improve in the future, how we could do that. But in parallel, we can still run relative location methods, and these relative location methods should actually decrease the uncertainties of the location between earthquakes, and this should emphasize which structures in the underground have been really activated. Okay, so if you want, in one hand, on the one hand, the model uncertainties make it difficult to see exactly where in depth the earthquakes are. But with these relative location methods, we could have an idea of what were the orientations of the faults which are activated and the extent of the faults which are activated. Okay, so we have to have a combination of both to be really able to image things underground. Then I'm finishing, and I would like to thank you for your attention.
I will present you the results of our borehole simulator that we achieved on the downhole pressure modeling at Vendenheim EGS site. Again, the borehole simulator the borehole simulator is in a way important also to understand the downhole pressure. And it is an important input parameter for many other reservoir parameters that we need to assess. In my presentation, I will first introduce a little bit in the borehole simulator, then I come into the technical part that consists out of two different models. The one is the calibration of the borehole model, and then the next is then the simulation, the model of the thermal stimulation at Vendenheim. And I provide you the perspectives. The mosquito, as I showed you before, was applied successfully to Reykjanes, and this is the application to Vendenheim. And we can achieve different goals with mosquito, and in this case, it's certainly not, it's a rather simple case in going into the injection scenarios. So production scenarios would be much more challenging than what we will see with the injection scenario. Nevertheless, the quantification of the downhole pressure is the issue that we have investigated. The simulation accounted for a borehole model that is split into four different sections and accounted exactly for the measured depth length and not for the true vertical depth, but for the measured depth. So you see the strong inclination, and this has, of course, an important impact also on the thermal heat exchange, because this one is much longer than in a vertical distance. And here you see that the uppermost part, the first 900 meters, we still have the drill string integrated in and a rather strong casing, and then it was a different casing development that has been that were accounted for, with going down to 8.38 inch in the lowest part. The calibration has been done on the hydraulic stimulation number 2 that has been done in Vendenheim on GT2. And this was the complete data set where we had downhole data and we had wellhead data. And the idea was that our model is able to match the downhole data recorded in assuming the wellhead data as boundary condition. In future, of course, it's a kind of forecast that you want to achieve with the borehole simulator, that you don't have to measure the we just have to measure wellhead data, but no downhole data. Now look into the comparison of this graph. You see pressure here normalized on the vertical axis, and you see time running up to roughly 33 hours on the upper scale, and seconds in the lower scale, and you have the temperature both on the injection on the measured data. The measured data are in black. The pressure is in blue, and the measured and the simulated temperature is in red. And you see quite nicely right in the beginning that there's a mismatch between the data in the black curve in temperature and the data and the modeled temperature data. And this mismatch is, in our opinion, of course, due to the initial condition in which the environment of the borehole has been strongly perturbed through the drilling process and through earlier stimulation and injection processes. But we see also a second case. In the middle of field, we see a very nice match here in the temperature and pressure. Here in terms of overpressure, here in terms of total pressure, and also temperature is matching quite nicely. But at the second part of the curve, there is a mismatch, it's a growing mismatch between the model and the data. And we have not been able to monitor this. And our assumption is that there might be some problem, might be also related to some sensors of the temperature data. So this is, we had to adjust those data on impact from the initial condition and an impact on the changing inlet temperature that was not monitored. Therefore, we tried to get an optimum fit, and this is, we increased here the temperature at the injection a little bit, and we injected the temperature of the production, of the second period a little bit. And this came out to have a very nice match here on temperature and on pressure. So this is in a way that we see that the data monitoring of the system is something that we can improve, and or that where we can also make a quality assessment of the injection data. I come back to this point again. I think I consider this to be a major issue. Another topic is, what is the thermal impact of the injection pump? So we tried to calculate, so the temperature data has been taken before the injection pump, but the injection pump itself had an important temperature effect, of course, because of the thermal losses. And we did this in two ways. One is assuming the pump efficiency, so the losses out of the pump efficiency, and a second was then out of the pump parameters, where we accounted for the energy and for the spinning per minute of the pump. Both the temperature is a function of here of flow rate, but flow rate cancels out in the real consideration. Nevertheless, I don't want to derive the whole procedure in here, but the result came is that the temperature increase through the injection pump is roughly maximum 2 Kelvin, so rather 1.5 Kelvin than 2 Kelvin. So this is the thermal impact of the injection pump, and this is something that we can see also, of course, in the simulation. Out of this calibration run, we right now went into looking into the so-called thermal simulation of Vendenheim. This was presented before, and I just show you the data, the wellhead data that we got, and more or less the thermal simulation had 5 different periods, ranging from 60 hours over 550 hours at phase 4 and 240 hours at phase 5. Flow, so you have time on the x-axis and normalized data on the y-axis, and you can see that in phase 1 flow in black was more or less constant. We had a step in phase 2, and we had, especially in phase 5, a rather complex situation. I will show you here the results for phase 1 and phase 5. that we achieved. So there were no other data collected. So we had to find a kind of a base model and identify a base model that looks to be convenient for a borehole profile. Now, first of all, we checked the impact of salinity. And the impact of salinity is low on temperature. This is what you see here, the red curve. It's rather low. So if you change salinity from 0.25 mole up to 4 mole, you will have a negligible impact here on the temperature history at bottom hole. The pressure at bottom hole, however, will strongly vary. So the strong variation of the total pressure is function of the molality of the pressure, of the injection fluid. The other is we have been looking on the sensitivity of the injection temperature. Again, what we had seen from the first case. And we checked different inlet temperatures from 7 degrees or 17 and 37 degrees. And I just told you that one of the unknowns is the injection pump, which we estimated to be roughly below 2 Kelvin. But you see just the opposite behavior when changing the inlet temperature. The pressure is more or less unaffected. The total pressure is unaffected. However, the temperature will be rather affected. So out of these data, we took a base model. A base model was the mean salinity of 1.7 mole, roughly 100 grams per liter, and the injection temperature of 17 degrees C. The roughness and the friction impact is, of course, changing per section, okay, and is always also changing per flow rate in the model. But what we see here is, again, the normalized pressure. Wellhead data, the data in black, again, as always. And here is the total pressure at the bottom of the casing at 3,300 meters TVD here. We measured, we calculated in MD, but here I give you the numbers in TVD. And the total pressure at bottom hole at 4,426 meters. And this here is the flow rate, the green is the flow rate that you can see. So this is the calculation that we can do, and where we established our base model. The base model then was applied for all the stimulation phases, and I show you the results out of this rather complex phase 5, in which the pressure, the flow rate is dramatically changing, and this is the green curve that you can see here. So we have a strong change in flow rate, and this is the blue curves are the changes, approximate changes of the downhole pressure. And again, out of the borehole model, the black one was the boundary condition, the wellhead data, and these are the calculations at bottom hole. And so we see the impact. Of course, the deeper we are, the higher is the pressure. And if you would go here a little bit more in detail and zoom up, we can nicely identify also what is the injectivity of the individual periods. Now, let me conclude. The model is rather sophisticated. I mentioned already that we are accounting for MD, for the measured depths, and not only for the TVD. And we also are accounting, of course, of the friction losses. Friction losses are an important factor that is a function of the flow rate and a function of the diameter of the well. And so this is a curve running with our base, that was run with the base model. And this here is a function, this is the pressure in bar. So we can have pressure losses up to 30 bars just through friction and these different flow rates in the model. And so this is, of course, a key issue. Once you want to dimension your well, you need to know how much friction losses you have in this well under the constraints, and they can be partly very complex of the borehole. So it is not a borehole science. Let me conclude. So we have successfully applied our model to the Vendenheim data, and out of the calibration already, but later on also in the simulation of the thermal stimulation, we got the feeling that we have a quite nice tool also for the quality assessment of the instrumentation. And so to bring together the instrumentation and the borehole, this is a kind of innovative approach that we can present in here. We hope that in future we can do these analysis together with our reservoir model. I thank you very much for your attention.
Good afternoon, everybody. My talk is about main geochemical characteristics of the deep geothermal brine at Vendenheim in Alsace. This work was done with the close collaboration of Fonroche and CFG, the subsidiary of Geothermal of BRGM. Well, Vendenheim site is in the Upper Graben, as said by Marianne. Two deep deviated wells, Vendenheim GT1 and GT2, were drilled in the granite, in the crystalline granite, at a depth of 5 kilometers. In this area, there are many oil wells, as you can see in the figure. For example, a oil field, but there are, I think, more than 1,000 oil wells with temperature colder than the geothermal wells. Near Vendenheim, there is also old geothermal well, Kronenburg, which was drilled in sandstone reservoir in Buntsandstein, and the other geothermal wells, as Landau, Sulz, Rittershofen, or also in Scheim, were drilled in the granite as the Vendenheim well. Two fluid samplings were carried out. One in March 8 in 2018 from the Vendenheim GT1 well, and the second sampling from GT2 in May 10, 2019, after water rejection operation and a short production test. Well, several fluid samples were collected, but among these samples, only 5 samples were analyzed in the BRGM laboratory. The selection was made with the lower pH values and higher conductivity values. TDS from the fluid range from 70 to 100 grams per liter, and the pH values are close to 7.10. Okay. Analytical methods were classical methods for water chemistry, ion chromatography, for example, inductivity, ECPAS, ECPMS, spectrophotometry, and the analytical precision for major was about 5%, and 10% for trace elements. Isotope analysis were made in BRGM laboratories with classical methods and corresponding analytical uncertainty. Well, in this diagram, you can see that most of the samples are contaminated by drilling fluids or injected brines in the wells. And the most representative fluid of the reservoir is a GT1 sampled in March 2018. You can see all these diagrams using bromine, chloride, and sodium. If you use also the trace elements, bromine, boron, strontium bromine, you can see the same trend, and the most representative sample is GT1 GT1 sample collected on March 2018. But this result must be validated by next campaigns of water sampling and chemical analysis. Well, we have a similar chemical composition of all the wells in the granite, but also the Cronenbourg well drilled in the sandstone, except for calcium concentrations. You can see that the calcium concentration are lower in the Vandenheim sample and also in the Cronenbourg sample. And you have also bicarbonates higher, but this value is probably due to the contamination of drilling fluids. And you have also a lower concentration of strontium in the Vandenheim sample. Well, for isotope results, we have similar trends than the chemistry. And you can see that there is a value, anomalous value in Vandenheim for carbon 13, probably due to the contamination of drilling fluid. Otherwise, all the values, isotopic values, are similar. You can see also the similarity of the Cronenbourg fluid and the Vandenheim fluid for isotope of strontium. You have close values. Well, if you wait for the origin of water, you can see for most of the deep brine discharged from the Rhine graben is a multiple origin of the Vandenheim native deep geothermal brine. It's a mixing between dilute water and evaporated seawater brine until allied precipitations. And also there is some slight dilution of halite from Triassic to the Oligocene. Well, this diagram shows the importance of temperature because we have in red the sample which indicates the higher temperature, close to 200 degrees. And for Bruxelles blinds, we have 190 degrees. And for the blue points, oil waters, the temperature are lower than 120 degrees. And you can see that potassium concentration is highest in the high temperature water as silica and or manganese, rubidium, cesium, but magnesium is in opposite is lower for decreasing temperatures as sulfate. The same for calcium, strontium. You can see that the high temperature waters are higher concentration of calcium, but you can see also the lower concentration for Van den Heim and Kronenburg waters compared to the other waters drilled in granite basement. Here in this diagram, you can see the lower and strontium concentration of Van den Heim compared to the other granite waters. For boron concentration, the boron is lower when temperature increase, and you can see with the isotope values that these values correspond to control of boron by halide at 225 degrees using the fractionation isotope equation. Well, if you see the chemical and isotope geothermometry, you can see that all the water indicate temperature close to reservoir temperature close to 220, 250 using different, the most classical geothermometers, and also isotope geothermometer that give similar values. And some of these geothermometers, as sodium lithium, magnesium lithium, or sodium cesium, are used for sedimentary basin and suggest the reservoir of the Van den Heim, but not only of Van den Heim, also in Scheim, Landau, is probably a sedimentary reservoir. Yes, you can see on the left, in the diagram on the left, that the influence of temperature on lithium concentrations. And you see that the lithium concentration increase with increasing temperature, and for lower temperature oil waters, the lithium concentration are lower. In the diagram on the right, you can see there are many sodium-lithium thermometric relationships, and the Van den Heim, Sulz and Insheim waters are in the line of the sedimentary basins geothermometer, sodium-lithium geothermometer defined by Caraca and Mariner for these water probably have sedimentary origin. And also the lithium isotope fractionation give values of lithium rocks close to minus 4% at 225 degrees. These values correspond also to carbonate sediments and not at signature of granite. Well, from these results, we can suggest that the brine from Van den Heim and Sulz and Insheim would come from a Triassic center of graben in the reservoir in the Butzsteinstein, and after this fluid migrates towards the border, to the borders of the graben, using a complex network of faults, northeast, southwest, but also northwest and southeast faults, with a temperature in the center of graben to close to 225, and after in the wells 200, the measurement, and also colder after migration. So main conclusions. This study has allowed determining the most representative reservoir brine, but it is necessary to have other fluid samples when the wells will be tested. The native geothermal brine is a sodium chloride type with a TDS close to 100 grams per liter and a pH close to 5, with a chemical isotope composition close to the other Rhine-Graben deep geothermal brine, except for calcium and strontium. And we can see also high lithium contents, interesting for the exploitation of this element. A multiple origin, mixing between primary brines formed by advanced evaporation of seawater and dilute meteor waters with contribution of sodium chloride dissolution from Triassic to Oligocene periods. Chemical and isotopic geothermometers give concurrent deep temperature close to 225 degrees. And some of the geothermometers and lithium and strontium isotopes suggest that the reservoir of this brine could be sedimentary and situated further east towards the center of the Graben, where Triassic Buntsandstein is deepest and hottest, with a thermal gradient of 40-60 degrees per kilometer, and at a depth of about or higher than 4 kilometers. And from the center, the geothermal brine will then migrate throughout a complex but still poorly defined system of deep faults to the Graben northwest borders. That's all. Thank you for your attention.
So I'm going to talk about the results from the life cycle perspective analysis. If I can control the screen. Yes. So the life cycle perspective part of the project was to do a life cycle analysis of the 2 demonstration sites, where we're looking at the environmental impact and the environmental cost of the 2 projects. So we're trying to find where in the life cycle the largest and most important impacts and costs are, and to see where the future low-hanging fruits can be addressed to be able to make a more environmentally friendly or better cost efficiency. So we're using the established life cycle assessment framework. We went through the cone scope definition, the life cycle inventory, life cycle assessment, impact assessment, and the interpretation part. So how we did it for this project, we divided the demonstration sites into 4 main parts. So the construction part, operation part, decommission part, and the product output. Although these 2 demonstration sites are together in this project, they are very different, at least in basically what the type of resource is, what is being produced, and how it's connecting to existing plants. So this all had to be modeled differently, and there are different approaches to that for the 2 sites. The main hindrance in this project for us was to be able to model the full life cycle of the demonstration sites since they are both in the development phase. So if you can see the 4 parts of the life cycle we have drawn here, only a few of those had already been done before our analysis. So what we did was to make a model for the 2 types of production. We did a model for the Reykjanes site and the Ventenheim site, based on literature reviews and different characteristics of the 2 sites. So when some of the construction phases had been completed, we collected the actual data from the Fonros and HS Orka partners and updated the model based on that. To be able to get a result that could be realistic, we did a evaluation of the data quality coming in, and based on the data inputs that we had to estimate, and based on that we got a distribution of different inputs using the pedigree matrix approach, and then we ran Monte Carlo simulations for 2 cases, one from the Ventenheim and one for Reykjanes. This was to have the base case for each site, and then we had like a range of results for the construction phase mostly. And then we did like a few scenarios where we looked at how it would how next steps would be, either if some realistic scenarios, some optimal scenarios to look at. So for Reykjanes, we took a look at the scenario based on where the inflow is coming to the well, and if it's coming from the existing resource or if it's coming from somewhere below. We didn't have real data, but we had data from the gas emission from the boreholes which are in place at Reykjanes today, and then we had the experiment at ITTP1, where we found used the difference between the emissions before and after that borehole had been drilled out, based on some articles. Then for the Ventenheim, we took a look at scenarios based on the connectivity. So basically just how much of an inflow we are getting to the power plant. And that affected the amount of electricity and heat that could be produced. So an example of the main inputs to the scenarios after having done the Monte Carlo simulation. So we have different power outputs for the Reykjanes, steam ratio, and the emission per steam, based on the difference between, as I said, the difference in the Krafla ITTP1 borehole. The results using this this setup gave us a range of basically impact per kilowatt hour. So we had the shaded part gives you the result of the Monte Carlo simulation for the 2 scenarios, and then we have 17.4 for the scenario 1. This is grams per of CO2 equivalents per kilowatt hour for the climate change impacts. So it ranges from 17.4 to 1.6, which is quite a lot of difference. It's also quite low compared to power production in general. What we did then was to take a look at where the impact is coming from. So for the Reykjanes site, most of the impacts are coming from the expected gas emissions from the borehole in operation. And for scenario 1, which was the scenario where we had connectivity to the existing reservoir resource, and the scenario 2 if we access some deeper resource. And we can see that the main difference is that we have this higher emission percentage in the scenario 1. For the Vendenheim results, the scenario 1 were similar. We had 15.4 grams, the mean result, down to 7.7 grams per gram CO2 equivalents per kilowatt hour. But the difference between these two sites is very apparent in the donut chart. There we can see that the emissions are negligible, and the most of the impacts are coming from the materials that are material and energy used to construct the boreholes. So it's the mud product, the drilling, the concrete, and half of the impact coming from the casing. This is basically the main difference between the two sites. We have more boreholes. We have very low emissions or negligible emissions from the Vendenheim because of the difference in the resource accessed. These results are then taken to and put into a monetary perspective. So we have cost data from Fonros and HS Orka, both true cost and expected cost in completing the demonstration site. And we added the externalities of the environmental impact, which was calculated with the life cycle assessment. And that resulted in a range of cost from 14 to 15.3 million euros for Reykjanes and 91 to 113 euros for Vendenheim. And this is the difference in the expected amount of boreholes needed to produce electricity and heat, and different demonstration sites. This resulted in the mean of the life cycle cost of electricity of 16.5 per megawatt hour per year for Reykjanes and 45 euros for the Vendenheim site. We can see that the well drilling is a huge part of the cost for both sites, and also for the Vendenheim site, the product plant is also significant. So for the summary, we have this difference in the life cycle impact of the two sites. Reykjanes has the biggest impact in the gas emissions, and Vendenheim has the most impact in the materials used to construct and make the boreholes. So in general, what could be done is to minimize the impact from Reykjanes is to add some carbon capture and either utilize or store the emissions. That would eliminate a lot of the overall emissions. As you could see, that 85% from Serran Area 1 was gas emissions. And this could also enable products being made that could utilize the carbon in the CO2 for either or various types of fuels or other products. For Vendenheim, the biggest opportunity for better environmental impact is to transition to more circular supply chains, so using more material and energy that decrease the impact, and emphasis should be using renewable energy during drilling in general, and use low carbon concrete if possible. Another interesting result is that when compared to other renewable energy production, these two demonstration sites are in the low end, and we can see the difference between the EU average and using coals to fuel a power plant or natural gas. So quite positive results in that regard. All right, that was it for me. Thank you very much.
People have time to grab a coffee or tea or something, and then we will convene the panel, and I would ask all the panel members to be on video, and we will screen the questions and ask people to address the questions that have been raised. I've had a number of comments that people would like to get the questions in some other format possibly as well. We will download, and actually I've extended the timeline on Slido. We have to test because even some of the people being questioned could go and answer the question, so we can prepare answers and add them, because we can archive everything and include that in the dissemination output from this event. So take a break, and we will try to screen the Slido questions, and then we will have to see who jumps in and tries to answer these questions. So a break until 4 o'clock, 5 minutes. Do you see the questions on a screen called Slido? Does it work?
We do not see. Yes. We do not see it on Zoom, but we see it in the website, of course.
Yeah, because I will have to share my. Is it a new share? I will have to share my whole other screen. Do you see it now?
Yeah.
Yeah, because now I'm sharing my big screen. This is a 40-inch desk screen. And now I need to control my remote basically from my phone. There are too many things going on. So we have questions. Some of them we can address. The highest scoring question is from Michael Krusevsky. And as you see, it is on the top of the list. Are the currently available well completion technologies, i.e. casing, cement, sufficient to enable long-term production from supercritical geothermal resource? So who wants to have a go at this one?
It could be that I can answer a little bit, but somebody else can come and complete. But at the moment, we are looking at scenarios like drilling down to magma and close to magma and get up supercritical fluids. And the main issue is, of course, the production casing composition or the cladding of the casing, the connectors. Actually, if we have some sliding ability or not, if we are getting materials with no thermal expansion or whatever we can think about, titanium, for example. But it is available, but it is cost issues as well. Regarding the cement, we have been showing in GeoWell and in DBGS that the cement itself is not the big problem. It's about the cementing technology, getting rid of the water content in the cement and the water pockets, and actually look at the procedure if we have reverse cementing or the normal used cementing technology, whatever we want to use. So it is pretty much in the discussion stages at the moment, but we see some improvements and we see some solutions.
So,
Thank you, Ingólfur.
so the short answer is no, but we are getting very close to it.
I didn't hear.
I said the short answer is no, but we are getting pretty close to.
Yeah, yeah.
Okay, you still see the question screen? I was not sure with what I did just now. You still see it?
Yes.
Yes,
Yeah.
we still see it.
Yeah, okay. Shall we move to another question by Paul Ramsek? That was the second highest voted for. That's actually again to Ingólfur.
Yes, it is. Actually, the cement job is done like in any other casings connectors. There's no difference, and the cement process has to be very good in this case as in others, but actually allowing or taking away the axial stresses in the casing will allow you to have, we believe, more stable casing. So I think that the common used procedures is applicable in this case, and that we can see that the cementation or the cement job is the same. What is going on when we move the casing or the casing is sliding into the casing connectors is that we have like a pipe inside a pipe. So the cement outside, the cement sheet will be steady, but the casing, the metallic materials inside will slide. So this is highly reliable on actually the friction coefficient. And if there are some chemical or some other bindings to the surface of the casing, that could mean that we are sliding with cutting. The shear stress actually will overcome the sliding. Sliding will be because of the friction coefficient, and the cutting or the shear stresses of the cement will be overcome.
Okay. Then we have a question about the Herringnet Methammer. Is Dennis still in the meeting? If he's not, then we will wait.
Dennis is there.
Is Dennis there?
Yes.
He probably needs to unmute himself. Any comments on this question, again from Paul Ramsak? It's about relation with the DEEPEGS project. Sorry about the spelling there, Paul. But anyhow, if Dennis would like to ask it, I can at least partially answer it, because I think in the call for the funding, there was a desire by the Commission to get new technologies that could have a breakthrough in costs in drilling. So we had this idea of the Methammer there, and maybe Ingólfur from work package 5, you were leading that work package, which is the technologies, where the Methammer actually was developed. It was supposed to be tested in Vendenheim, had never materialized. So the plan was to develop a new technology that could speed up and lower cost of drilling. We noted in the LCA that the cost of drilling was quite high in both sides. Any further comments from my colleagues that know more about it than I do? I think we can try to write up more on this in the review for the meeting.
Well, Sigurður, you are correct. It was to be tested in a hole in Vendenheim or so, in some of the Vonros wells. So that was a connection to the DPDS.
Yeah. And cost lowering kind of new technology trial. So on top of the screen now we have from Stephen Onsha. It's for drilling directional. Have the studies been able to quantify the deep fracture density and orientation, and what is the future implication for drilling deep directional wells? Anyone liking to take this one on?
Yes, we can take this.
Okay.
Right, so for the IDDP2, we have done this exercise to evaluate the deep fracture densities and so on. However, the confidence level, like we mentioned in the main presentation, it's pretty low. However, I can give you some numbers, especially now when I've seen a bit more on what you guys or the other groups were working and talking about. So for a confidence level of about 70%, the density fracture at 3,400 meters in IDDP2 is 0.28 centimeters. So that's meaning that every 30 centimeter you have a fracture, right? If you lower the frequency or the confidence level, then of course the counts of fractures may increase dramatically, right? So it's really depending how you set your resolution and accuracy on the borehole images, and where is the trade-off between the laboratory study and resolution accuracy of what you get from the borehole data. So that's for the first part of the question, and I think this exercise can be done for any geothermal well. When it comes to directional drilling, one aspect that rise up here is that the borehole images they show petals, right? So actually those structures in the borehole images, they are intersection with the sheeted dike, right? So it may tell you a story about the angle of attack into certain fractures or certain substructures, if you wish, into in the subsurface that you may intersect with with those kind of directional drilling. Now, depends how you look at it, and I will say that it's very important to understand the orientation of those structures in order to adjust your angle of attack in such that you go perpendicular of the fracture. Otherwise, you may risk a deflection of the drill bit, and you will deviate from the well path that you are aiming for. I hope this kind of covers the question.
Okay, thank you. I now learned how to put the question that we are phrasing. I think we take the next one. Thanks. So there is a slight time delay. There's a question from Tobias. I'm trying to put it on top. To Marianne Peter Borri, can you take this one on?
Yeah, thank you, Tobias, for this excellent question. Actually, it's a good question because if you have ritual quartz, that means that you have enough space to growth of the minerals. So if you have space, you have you can have flow inside the discontinuity. Actually, I think I've been too fast in the explanation of why we had impermeable area in this zone. We have actually ritual quartz, but it was precipitation from older circulation probably, and we have also clays and no losses in this part of the drilling. That's why, and probably these two last are the main clues that mean that we have no area. So ritual quartz is a fact. We can see them. We had previously circulation in this area a long time ago probably, and now it's filled with other minerals like clays and so on that make this part impermeable.
Okay, thanks, Marianne. Anyone else wanting to comment on it? Because I now have learned to archive the questions when they have been replied to. So I will archive this one. And this one from Omar to Sierenberg. I think Sierenberg is not in the meeting anymore. So shall we just send it on to him and ask him to reply to it in writing? Or anyone else wanted to comment on it, Guðmundur?
No, we should just send in the question so he can reply.
Yeah, so we leave it on there. Then there is another one to Anthony. It's on top now. Anthony, are you in the meeting? Can you comment on this one?
I'm still here.
Yeah.
I can provide a brief answer, but maybe Marianne can complete my answer if. For the in-situ stress tensor, it has been evaluated for the Van der Leyen demonstrator using the analysis of the borehole breakouts with respect to the well trajectory and the mesh losses during the drying.
Yeah, maybe just add a few words about that. Actually, in the first well of Van der Leyen, we had caliper and images in the sedimentary part of the well. So we will be able to estimate the stresses with some assumption, of course, from the breakout and the drilling-induced fractures, but it's not in the basement. So to complete, we use from source mainly and from literature review, of course. Yes, it's based mainly on the data on the sedimentary part.
Okay, so we will try to put this one down, and then we can, there is one from Þorbjörg to Emmanuel.
Yes. So there are source mechanisms which have been computed by Roche, but they did not send me anything about this. As far as I remember, they were following more or less the alignments we could see from the clusters. And actually this was consistent with the main orientation of the fault there, which means that it's north, northeast, southwest main direction. And for the faulting process, as far as I remember, there was normal faulting and strike slip. That's what I remember from the images. But I cannot tell you everything in detail right now because I have not the data myself. I can ask for some information about this. Only a few earthquakes, focal mechanisms have been computed, so not everywhere, not all the events, of course.
Okay, thanks. We will review the questions as well after the meeting, so I'll share a document with them to the speakers. So we go then to Gunnar Skúlason Kaldal. On top, there is to Þorleikur. I'm not sure if Þorleikur is in the meeting.
Yes, I'm here.
Yeah. Okay.
I'm being served. Getting coffee. Well,
nice.
Gunnar, thanks for the question. I'm really not sure how HS Orca had planned this, but there was a discussion of doing something like this. I think you are referring to some online. Some material monitoring or something like that. There was a discussion of sticking some coupons into with different material. Some of them, look alike to the material we use in the well itself. But it was not fully decided, and also we discussed it on a great deal if it would be beneficial to put something into it, but creating turbulences in the flow can some cases do more damage than provide some answers. But it is possible that the HS Orca have some written down procedures of material evaluation monitoring. You are talking about elevation monitoring. Yeah, that would be done. Sorry, I thought it was some evaluation monitoring of the material. But of course, there is some online monitoring of the wellhead of the elevation. That is.
Okay, so we'll go to the next one. It's regarding RN15. Have you evaluated the effect of supercritical fluid due to extreme heat capacity on cement casing? Anyone wanting to take this one on?
I can try, but we have been looking at the cement casing connection, and especially due to the sliding ability of the flexible coupling. So actually what we have been seeing is that we have been monitoring if the cement will stick to the casing or the casing will slide, and how it will be when the cement goes up to these temperatures. And in that case, we have looked at the cementing samples we have from the IDTP 1 up to 450 degrees. So actually it has been evaluated to a certain extent, of course, yes.
Okay. So we could archive this one as being replied to. Then I'm not sure how. I think I'll just archive this one. Then we have a question from Val Maverick. If I put that on top. Anyone having a reply to this one?
I assume this might be for me. About the fluid chemistry. There are no samples from these two aquifers. There are no samples from the wells. So all the work that has been done is hypothetical. On the other hand, the samples or the fluid chemistry presented by Sierenberg and Bali is based on fluid inclusions from the drill core. But there has been no downhole sampling of the fluid. So this is, all educated guesses.
And any further comments on this point?
If I can add to this, it's just ongoing. We will take a look at fluid inclusions from shallower cores. It probably will happen this year or next year, so we will do know a little bit more.
Okay. Then we have another question from Jesse Nikobi. Anyone knowing about this numerical simulation? Is it for KIT, or who can take this one, or is it for Alessandro?
It's not for me.
Maybe I can.
Yeah, okay.
We have performed a numerical simulation using discrete element method, and the code is embedded in a finite element method. No, it's not a real FEM-DEM, but it's a DEM embedded in the FEM to have to put away the boundary condition. It was to evaluate, to assess the thermal stimulation in IDDP2. And it is published for now. Published. Yeah.
Okay. I'll just put this one very shortly on screen. Just that the people are interested and saying thank you. So I'll just close that one as well. It's from Tobias. And then it's a question to Guðmundur.
I don't know. But I think what we have learned is that we can surely inject into the supercritical regime
And the question is how long can we produce them? So I just think we do need to test it. But we can inject into it and re-inject fluid, and I think they would keep quite open for quite a long time if you have the sort of injection. But don't know about the rest.
So anyone else commenting, or we close this one? Then there is another one from Val. Not sure. Yeah. Regarding the course, I'm not sure if Sirenberger would get this one, or is it Enika or Jökulmundur that can?
Well, my suspicion is that this kind of alteration happens just due to fluid migration on grain boundaries. So it's not a channelized flow, it's a pervasive flow which happens in grain boundaries or along grain boundaries, and it eventually, probably a little bit more slowly, but it eventually leads to alteration.
Okay, thank you. Then there is a question from Omar. I'm sure that there is a short lag in changing the screen. Sorry about that. Any takers for this question?
I think Eniko can answer this.
Yeah, I can try to answer this. So, of course, we are very lucky in these drill cores that we have a bunch of mineral pairs which can be used as geothermometers. And we have seen that some of the minerals are actually recording probably the peak metamorphic temperature because the closure temperature for diffusion is high in those cases. But there are some mineral thermometers which are in which the diffusion rates are much faster, and there is diffusion also at a much lower temperature, which record the cooling sequence. So like the oxide-based thermometers, for example, which give a temperature of approximately 600 degrees, and that's what we see in the lowest temperature quartz, and that's what we see in the fluid inclusions. Of course, we don't know exactly when this last fluid inclusion generation was closed in these minerals. It can be 100 years ago, it can be 1,000 years ago. We don't really have a good grip on timing, but I think the most plausible temperature is these 3 independent thermometers based on the oxides, the quartz, and the fluid inclusions. They all point to the same temperature, and it is probably very close to the temperature at the bottom of the borehole. It can be a little bit colder, but not significantly more.
Okay, thank you, Eniko. This was. Then we have one that is cropping up because it's being loaded up, the scale, to Guðjón. Are you still with us?
Yes, I'm here. Can you hear me?
You see the question?
Yes, can you hear me? Yes, the question. It could be a case embedded. It could be. We don't know what it is. So, and we see that the temperature reaches the fiber optic more faster at this step. So some kind of opening or damage is definitely one option. Until we know what it is, it's kind of hard to say. But conduction of the production casing. I don't recall we had any problems at that depth of the production casing, to my memory. And we need to check, but I think this is within the sacrificial casing from the well. It's the 7 inch. So we have quite a lot of casing layers at this location as well. Maybe makes it unlikely that we have a casing damage. So we could argue both ways. So until we know, it's kind of hard to say.
Okay. Thank you. That's a question for Benoit that is coming up there. Benoit, can you reply to Thomas Renz on this point?
Okay. Yes, thank you, Thomas, for this question. So no, on the crack density plot, it is not indicated that 80% of the crack volume occupy the rocks. So it doesn't mean 80% of porosity because of cracks. In the crack density calculation, you assume that the cracks are elongated as penny-shaped cracks or spheroidal cracks, and it is the case in these calculations. So to get the porosity, you need to multiply the crack porosity, you need to multiply the crack density by the crack aspect ratio, and that will give you quite low porosity because aspect ratio is in general very low, and it is the case in this example.
Okay, thank you. Then we have a fairly recent question coming in from Gunnar Skúlason Kaldal, addressing Martin and Guðjón regarding fiber.
Yes, I think that we start. We're still on a learning curve, but with the extent of the changes we've seen, we don't expect.
Can you get closer to the mic, please? You break up a little bit. We don't hear you well.
Is this better? Can you hear me better now? Okay, right. The stack of the changes we've seen and steam emitting at some point from the well, I couldn't see that the formation temperature would have huge change. It would be rather stable throughout. But as we inject cold air into the well, we can see cooling closest to the wellhead. So we see kind of dynamic changes to what we're doing. So I don't believe we would see that in the formation temperature. It would be kind of close to constant, I'd say. But Martin has maybe more insight into the technology itself and how that could be affected. But all of the changes we've seen are kind of representative and can be explained with other parameters.
Any other comments, or we go to the next one?
Yeah, also I have nothing to add to this. I think Guðjón is right.
Okay.
Maybe a comment from me. This Chelsea, the sample is quite bad, so maybe we will include this in the written answers as well after the meeting.
Okay. I'm not sure how many, because we are now past the half an hour. How willing is the group to continue? We have quite a few questions, but we are getting close to the end of them. Are we willing to spend a few minutes and try to clear most of the questions? The next one is for Robert Sinneberger, so I think we'll just put it in the archive. Unless somebody wants to reply to that one, but I don't think, I think it's for him. So we just put that in the archive. Then we have another one from Val Maverick. regarding the obstruction in the well, again, I think Guðjón or actually this question more or less has been replied to.
Yes, I think it's kind of the same question as before.
Okay.
I know it's not related, but we've only found the social media because camera down.
Okay. So we just put this one in there. And then we have another one from it's for the fiber optic.
Yeah, I believe that's the plots I showed earlier. That was this sudden kind of release when this obstruction that, as we interpreted it suddenly released, and so the entire well column was heating up a bit, and this gradient down there, this step solved or dissolved, wasn't there afterwards anymore. So kind of a breakthrough of the steam.
Okay, thank you. And we have another one.
I could maybe answer this one. In the logging trip, which they hit the obstruction at 777 meters, just about 780 meters, it turned out that we locked the temperature locked it down to 760 meters, and the well was completely dry. Okay. So it means that the plug was tight when it was locked. Okay.
Thank you. This is just a correction from Gia Wang to Thomas. So probably you can deal with it later in bilateral, and if there is a correction needed for the slides, it can be done before we post them on the website, because we probably will put all the slides to the DEEPEGS website as PowerPoint PDFs. So they're accessible there, and then later on the video with the proceedings. Then we have another one from Gia. That's there are two left, both to Sturla. Is Sturla with us still? If Sturla has left, we will ask him to reply to this question in writing. It seems that Sturla is not in the meeting anymore. So we will ask Sturla to address these questions in writing and add them to the proceedings of the meeting. I want to quickly see if I can. The polls were not really very popular, and I'm just going to show you, but whether it's yeah, this is the current live poll. It's just to collect phrases. It's obviously very few participants, only 9 people, so it's not relevant. And I heard from someone saying this was kind of mute, how healthy we think the industry is. So, and there is another one that has not been launched, which actually I will launch now, and people can just reply in the next couple of days or something. It's regarding this webinar. It's kind of a popularity, and also Zoom will send out a survey following that we close the recording. So all the participants will get a survey. But this is for our own purposes, just to see how likely, because we want to post it on YouTube or Vimeo or some other platform. We need to think how likely is it that it will draw in crowd. We had over 360 people registered for this event, and some of them, obviously, because of time differences, are not active. I think maybe Hjalti can confirm that we had up to 170 people in the meeting at one time. I'm not sure how many were because I couldn't see the participants register when I was sharing my screen.
This is correct. This is correct. We had quite a lot of participants. Basically, in the morning around 10 o'clock or 11, that was the biggest audience, up to 170. That's correct.
Yeah. So we'll just leave this poll open, and I think it's for us now to decide from the experience we have also gained that maybe these meetings have to be put into not a whole day session, but into kind of 3 to 4 hour blocks, because to have attention from everyone, that's something that we will have to think about. There were also questions that I put aside for the moment that were targeting Von Ross, as we didn't have Jean-Philippe Soule with us. He was planning to call in. We will ask him to address those questions by writing, or we have a bilateral discussion with him. Lionel Boucher, I'm not sure if he is in the meeting anymore, but for me, I'm handing over to our coordinator to say some few wise words at the end, and if any panelists would like to say anything before we close the recording, please, the floor is yours.
Okay. I'd just like to end this with saying thanks to all the presenters and thanks to all the audience. It has been a long day, a tiring day, and personally I am pretty pleased with the result. So this is a substitute for a real meeting. I like meeting people shoulder to shoulder and talked in the break sessions, but this is something we live with for the moment. And so I say thank you all, and I think we should just close the meeting.